Good afternoon and welcome to NASA headquarters in Washington. I'm NASA Public Affairs Officer Trent Parado. And thank you for joining us today for NASA's Exploration Forum on the Human Path to Mars. It's a really exciting day for us here at NASA because today we get to spend a couple of hours this afternoon on one of people's favorite topics when it comes to space, and that's sending astronauts to Mars. What's the path to get humans to Mars? What do we need to do it? We have a really unique opportunity today to hear the answers to those questions from NASA leadership from across the agency. So you'll hear directly about NASA science currently on and around Mars, some of the new planned science, new technologies currently in development, and our ultimate plans for the human exploration of Mars. For those of you watching from home, I'd encourage you to find out more information about NASA's Human Exploration Program at www.nasa.gov/exploration. If you're joining the conversation online today, you can do so with the hashtag Mars. If you have questions during the event, we'll stop for Q&A at about halfway and try to get to as many of those as possible. You can let us know your question on Twitter using the hashtag AskNASA. We have an incredibly impressive lineup of speakers today here to tell you much more about the human path to Mars. But first, I'd like to show a short highlight video that showcases some of the things we'll be talking about in more detail. If we could roll that, please.
A big rocket ship. We're having fun. 3, 2, 1. Let's go! We're going to the stars. Yeah, look at the rocket ship.
Mars, a rich destination for scientific discovery. As we expand our presence into the solar system with robotic and human exploration, the formation and evolution of Mars will help us learn more about our own planet's history and future. In its past, the red planet had conditions suitable for life, and future exploration may uncover evidence of life, answering one of the fundamental mysteries of humanity. Does life exist beyond Earth?
At NASA, we're reaching for new heights so that we remain the world's leader in space. We're pioneers, and we always have been, and we're building on that pioneering spirit in science and technology so that we make the world a better place and we create jobs right here on Earth.
NASA is developing the capabilities needed to send humans to an asteroid by 2025 and to Mars in the 2030s.
We're building something that can go lunar, we can build something to go to an asteroid, we can go to Mars with this. This is the next step that we've been looking for since the Apollo era.
Robotic explorers have studied Mars for more than 40 years. NASA's path for human exploration of Mars begins in low Earth orbit aboard the International Space Station. On board the orbiting laboratory, astronauts are helping us prove many of the technologies and communications systems needed for human missions into deep space.
Well, the crews right now on the International Space Station are using this wonderful outpost to help us get farther and farther into space, to asteroids, to Mars eventually. I think the science on station is making incredible breakthroughs that are going to help us make life better for people right here on Earth.
We and our other international partner crewmates are working off the planet for the planet.
NASA, along with our international partners, conducts scientific research every day here on the station as we use this orbiting laboratory as a stepping stone for future deep space exploration.
In tandem with space station research, NASA will send a robotic mission to capture and redirect an asteroid to orbit the moon. Astronauts aboard NASA's Orion spacecraft will explore the asteroid and return to Earth with samples. This experience will help NASA test new systems and capabilities, such as solar electric propulsion, which will send cargo as part of human missions to Mars. NASA's new Space Launch System will enable these proving ground missions to test new capabilities. Human missions to Mars will rely on Orion and an evolved version of the SLS, which will be the most powerful rocket ever flown.
With Orion and our heavy lift space launch system, we're going to send humans into space farther than they've ever gone before. This year's Orion test flight will be the most aggressive for a human spacecraft in more than 40 years.
Apollo happened before I was born, so this for our generation will be the exploration missions that we get to see in our lifetime.
A fleet of robotic spacecraft and rovers are already on and around Mars, dramatically increasing our knowledge about the red planet and paving the way for future human explorers. Future missions, seeking signs of past life, will demonstrate new technologies that can help astronauts survive on Mars.
I think some of the most amazing things that we're learning are actually how to be really good detectives on another planet, which is a really difficult job.
Engineers and scientists around the country are working hard to develop the technologies astronauts will use to one day live and work on Mars, and then safely return home from the next giant leap for humanity.
Through advanced aerospace technologies used in everything from modern aircraft to suborbital rockets and the commercial vehicles servicing low Earth orbit today, we're building the machines to take us farther into the high frontier. NASA is here to raise the bar for human achievement. We're a community dedicated to research and discovery in service to society. We have a responsibility to the future generations, to the future generations of engineers, scientists, technologists, explorers. That's our challenge.
We're having fun!
So let me just thank NASA TV and our colleagues from around the agency for that excellent video showcasing some of the work that's happening around the country. So now it's my privilege to introduce our first speaker. NASA Administrator Charles Bolden became the 12th NASA Administrator in July 2009. As Administrator, he leads the NASA team and manages its resources to advance the agency's missions and goals. He's a retired Major General of the United States Marine Corps. His 34 years in the Marine Corps included 14 years as a member of NASA's Astronaut Office. He's traveled to orbit more than four times aboard the Space Shuttle between 1986 and 1994, having commanded two of the missions. He was pilot of STS-31, the flight of the Space Shuttle Discovery that deployed the Hubble Space Telescope in 1990. Of course, as Hubble extended our senses farther into the universe to see farther than ever before, we of course look forward to hearing from the Administrator his thoughts on our plan to send humans farther than ever before into the solar system as we embark on the path to Mars. Please help me welcome Charlie Bolden.
Thanks very much, Trent. As I look around the audience here, I want to welcome everyone to this Exploration Forum. Even though I see a lot of people I know and recognize from before, I'm still going to make my comments anyway, because Charles Scales is back there and he didn't hear this before. So Charles, this is for you. And there may be a few others. This is your opportunity, even if you're a NASA employee. I mean it. It's your opportunity to see, hear, discuss, and learn how all of NASA's exploration resources are supporting our big goals of a human mission to an asteroid and human missions to Mars. Some of you may have read, some few of you may have read an op-ed by Dana Milbank the day after I kicked off the Humans to Mars over at GW, and I found it to be very interesting, as did my 14-year-old granddaughter, McKaylee, who was quoted quite often by me in that forum. When I sent her the piece so she could see how Dana Milbank, you know, a world-renowned journalist, had written her name in an op-ed, she said, that's really cool, except he didn't agree with anything you said. I said, well, you're very astute, McKaylee, so I'll go back and try it again. So I'm back here to try it again today. You know, with Mars making its closest approach to Earth since 2008, a few weeks ago, and currently appearing as the brightest body in the eastern sky during the month of April, this is an ideal time for this forum. As the red planet draws nearer to Earth, NASA, with your help, is drawing nearer to our goal of sending humans to Mars. Today, you're going to get an update on NASA's path to Mars from some of the leading experts at the agency, including Ellen Stoffen, NASA's chief scientist, Bill Gerstenmaier, associate administrator for our Human Exploration and Operations Mission Directorate, and John Grunsfeld, head of the Science Mission Directorate. After you have a chance to hear from them and others, ask questions. Robert Lightfoot, our associate administrator, is going to give you a wrap-up. But this day is really about you. Nothing we want to achieve can succeed without all of you, the American people. And I say that recognizing the fact that the vast majority of the American people are not seeing this and will not see this. But many of you here who represent the media, you are the eyes and ears for the American people. So we count on you asking really poking, probing questions today. I want to make sure that we can hear your thoughts on the best path forward. But let me set the stage by reminding us of why we are all here. While humans have been fascinated with Mars since the beginning of time, there are a number of very tangible reasons why we need to learn more about our closest planetary neighbor. For one thing, Mars's formation and evolution are comparable to Earth's, and we know that at one time Mars had conditions suitable to life. What we learn about the red planet may tell us more about our own home planet's history and future and help us answer a fundamental human question: does life exist beyond Earth? While NASA has been on a path to Mars for decades, and our earlier Mars rovers and orbiters, President Obama made a critical national policy statement in support of our strategy on April 15, 2010, during a visit to the Kennedy Space Center when he challenged NASA and the nation to send humans to an asteroid by 2025 and to Mars in the 2030s. The U.S. National Space Policy, set in 2011, further supports these goals. Over the past several years, NASA has been developing the capabilities to meet these goals through a bipartisan space exploration plan agreed to by the administration and Congress in the 2010 Authorization Act and embraced by the international space community in the 2013 Global Exploration Roadmap. While robotic explorers have studied Mars for more than 40 years, NASA's path for the human exploration of Mars begins in low Earth orbit aboard the International Space Station, our springboard to the exploration of deep space. As we speak, astronauts aboard the ISS are helping us learn how to safely execute extended missions deeper into space. We are guaranteed this unique orbiting outpost for at least another decade by the administration's commitment to extend the ISS until at least 2024. This means an expanded market for private space companies, more groundbreaking research and science discovery in microgravity, and opportunities to live, work, and learn in space over longer periods of time. As most of you know, we're working to return both cargo and human launches to the ISS to American soil. The President's 2015 budget supports the administration's commitment that NASA be a catalyst for the growth of a vibrant American commercial space industry. Already, 2 American companies, SpaceX and Orbital Sciences, are making regular cargo deliveries to the space station. While the Russian Federal Space Agency, Roscosmos, remains a strong and reliable partner, later this year, NASA intends to select from American companies competed to send astronauts to the station from American soil. If Congress fully funds our 2015 request, we believe we can do this by the end of 2017. Our next step is deep space, where NASA will send the first mission to capture and redirect an asteroid to orbit the moon. Astronauts aboard Orion spacecraft will explore the asteroid in the 2020s, returning to Earth with samples. This experience in human spaceflight beyond low Earth orbit will help NASA test new systems and capabilities, such as solar electric propulsion, that we'll need to support human missions to Mars. Beginning in 2017, NASA's Powerful Space Launch System, or SLS rocket, will enable these proving ground missions to test new capabilities. Human missions to Mars will rely on Orion and an evolved version of the SLS that will be the most powerful launch vehicle ever flown. A fleet of robotic spacecraft and rovers already are on and around Mars. They are dramatically increasing our knowledge about the red planet and paving the way for future human explorers. The Mars Science Laboratory Curiosity rover measured radiation on the way to Mars and is sending back radiation data from the surface. This data will help us plan how to protect the astronauts who will be exploring Mars. Future missions like Mars 2020 rover, seeking the signs of past life, also will demonstrate new technologies that could help astronauts survive on Mars. Engineers and scientists around the country are working hard to develop the technologies astronauts will use to one day live and work on Mars and safely return home. It's important to remember that NASA sent humans to the moon by setting a goal that seemed beyond our reach. With Mars as our focus, we are steadily building the capability to enable human missions to Mars. The challenge is huge, I will admit, but we're making real progress today as a radiation monitor on the Curiosity rover records Martian radiation environments daily that our crews will experience. Meanwhile, advanced entry, descent, and landing technologies needed for landing on Mars are ready for entry speed testing high above the waters of the Pacific Ocean in June. Orion is finishing preparation for a heat shield test in December. And in New Orleans, we're beginning to manufacture flight hardware for the heavy lift rocket necessary for Mars missions. We're counting on the support of Congress, the scientific community, and all of you to help us realize our ambitious goals. The future of space exploration is as bright as Mars shining at us in the eastern sky this month. But it will be up to all of us believing and working together to achieve our ambitious goals. We're embarked on an exciting, incredible journey, and we hope you'll choose to be a part of that team. With that, I'd like to thank you, Trent. I'm going to give it back to you, and one quick reminder, if you don't have a copy of the scorecard, get one. Put it in your man purse, as I told our NASA employees, if you happen to have one. If you're a woman carrying a purse, big or little, you can fold it, you can put it in your inside pocket, memorize it, ask lots of questions about it so you're conversant on it, and turn it into your 30-second elevator speech, whether you like us or not. So thanks for coming out today. Thank you.
Thanks, Charlie. We do have copies of the chart Charlie just showed here printed in the audience, and for those of you at home, you can find a printable copy of that at nasa.gov/exploration. Many of you will know our next speaker, John Grunsfeld, as the NASA Associate Administrator for the Science Mission Directorate, position he took in January of 2012. Previously, he served as the Deputy Director of the Space Telescope Science Institute in Baltimore, managing the science program for the Hubble Space Telescope and forthcoming James Webb Space Telescope. Others of you may know that John was a NASA astronaut. He joined NASA's astronaut office in 1992. He's a veteran of 5 space shuttle flights and visited Hubble 3 times. During these missions, he also performed 8 spacewalks to service and upgrade the observatory. But if you're on Twitter, I hope all of you will get to know him. And if you're not following him already, at SciAstro, that's SCI for science, a scientist and an astronaut is here to tell us about bridging those two worlds as we explore Mars. Please help me welcome John Grunsfeld.
Thank you very much, Trent. When Administrator Bolden was selected as an astronaut, which, as I remember, was class of 1984, pardon? 1980. I guess Mike Full was 84. 1980, he was told that he would be a member of the class of astronauts that might set foot on Mars. Following in his footsteps in 1992, I was selected in the 14th group of astronauts. And like so many classes before me, we had Mars on our patch because we were told we would be the class that would be the explorers to set foot on Mars, at least some of our members. And one of our members of the class of 1992 is on the International Space Station right now, Koichi Wakata, classmate of mine from JAXA. And while I'm not going to set foot on Mars personally, I'm here to tell you that we all are on Mars right now. We have a really incredible science program. Charlie mentioned the Curiosity rover. I'm going to walk you through a little bit of how we all are on Mars right now and how classmates like Koichi, are on their way to Mars, even if not personally, they're paving the way. I also show this Mars globe, as you saw in the video, because it's an excuse to show Hubble images, but I'll move on. Maybe? We tested this earlier. Okay, next. So we've actually been on Mars, or observing Mars, for 50 years. This is 1964, Mariner 4, and we started to get a view of Mars that was very different than those from science fiction or our imagination. It was a Mars that at that time was more reminiscent of the Moon than of Earth. We continued to explore Mars. Next slide. Yep. With a series of orbiting missions that gave us pictures of Mars that, while they showed a barren Mars, clearly indicated features that appeared to be evidence of past floods, of water flow. Next. And then Viking, when we landed on Mars with 2 great observatories to Mars that indeed revealed Mars as what appeared to be a lifeless desert. Enormous amount of information, a lot of controversy too about what was discovered, the possible existence of life or of some kind of metabolism on Mars, but we pressed forward. Next. With the exploration of Mars, with Sojourner in 1997, our first very capable rover. Spirit and Opportunity. Opportunity is still roving today. Phoenix, which landed near the polar cap of Mars, and we were trying to find out whether there was water, and we landed on a glacier. And Curiosity, which is, of course, all of you know, is roving today. Next. So where are we on Mars today? Next. So here we have Curiosity and Opportunity. We have Mars Odyssey orbiting Mars, Mars Reconnaissance Orbiter orbiting Mars, our partners in the European Space Agency with Mars Express. We really are exploring Mars today. Next. Keep going. So here's Curiosity's selfie from the Mars hand lens imager taken in a mosaic with the sun in the background. And it does look a little bit desolate, but Mars hasn't always been that way. Next. Curiosity has been very busy. This is a view of Mount Sharp. We're slowly making our way towards Mount Sharp. And along the way, Curiosity has made a number of incredible discoveries. Next. We have already discovered that Mars once, billions of years ago, was a happening place. It had standing water, probably fresh water. John Grotzinger, the project scientist, said it was probably such that you could drink it. And the mineral content showed that it was basically neutral pH and lasted long enough that it could have supported primitive life, microbial life, for instance, if it existed on Mars. And so we've answered the question, was Mars ever habitable? We haven't answered whether there's life there, but we have answered that question. And so Curiosity is pressing on. It's roving, it's drilling, it's investigating. It is a surrogate for a planetary scientist on Mars. Next. This is where Curiosity is today. If you look in the middle of the photo, there's kind of a blue dot there, and you can see some tire tracks if you look really closely. That's Kimberley, where the Mars Curiosity is right now. Next. So science has been coming out like crazy. I want you all to continue to pay attention. We have explored Mars habitability. Now we're looking for any kind of signs of carbon, perhaps, in the rock record that might be an indication of fossil evidence of past organic activity. Next. And so what have we learned that is interesting for human exploration of Mars, future human exploration of Mars? Next. So, of course, an opportunity to show another Hubble picture, and we know that Mars has weather. We know that it has polar caps, it has clouds, it has sandstorms. So it is a very active planet like Earth. Next. This is a picture from the Opportunity rover looking up at some of those clouds. Next. And we know that Mars does indeed have a very thin atmosphere, does support winds, it supports weather, but it doesn't support the ability to have liquid water on the surface. Next. The pressure is just too low, and so it would sublimate immediately off into the atmosphere. Next. But we get weather reports, and sometimes it's cold enough and humid enough that, in fact, you might expect to see frost. So we know there's water, a relative humidity that could be extracted if you wanted to have water. The temperatures sometimes are quite temperate. This is today on Mars. It's the REM instrument, the Rover Environmental Monitoring System, which was contributed by the Spanish, and thus the Spanish language. But we see that it's about 8 hectopascals, so that 1%. Relatively cold day on Mars, minus 24 C. Daytime temperature, minus 82. Night, Mars rotates at about the same rotation rate as Earth. But sometimes it's 10 degrees C. Quite habitable for humans. I like to climb mountains in these kind of temperatures. Next. We also know that, as I said, there's water in the atmosphere. Most of the atmosphere is carbon dioxide. Carbon dioxide we could extract oxygen from. We could use the carbon dioxide for plants to transpire. Argon, which is really interesting because we have argon on Earth at about the same percentage. Nitrogen. Nitrogen is very important. The fact there's nitrogen on Mars means that you could have fertilizer. Nitrogen in our atmosphere is the major component. It means you could extract that to produce an Earth-like atmosphere. Next. And of course, water on Mars. Now, people say we've recently discovered water on Mars. Well, in fact, we've known spectroscopically about water on Mars for many, many decades, since we started doing spectroscopy with telescopes. But now we're actually, this is from Mars Reconnaissance Orbiter, able to study, the polar caps, carbon dioxide and water ice glaciers, and we know a lot about the history of Mars and water on Mars. Next. This is something really striking. These are a series of images from Mars Reconnaissance Orbiter looking down on gullies, and something in these gullies is seeping out and resident for some long periods of time, seasonally. So in summer, something's leaking out. And if it's very briny water, it actually could survive at the low temperatures and pressures for a little while before it's sublimated. And so some scientists think that underneath the Mars surface is some kind of a glacier that's periodically melting and releasing that salty water and would then be accessible. And if there's life on Mars, this could be some place that it could ephemerally exist. Next. And of course, we see that on upper left on Mars. Now, this is from Mars Express in many different places that look very much like the similar types of gullies that we see on Earth. And so we're able to go and explore those, try and understand those on Earth to compare to Mars, because Mars is really a very similar place to Earth. That's the message I want you to take away, is that Mars is really very much like Earth. Next. Lots of evidence for accessible water. The upper left is from Phoenix. We dug a little bit in the Mars surface, and lo and behold, we find water ice, which over time sublimated. We occasionally see meteoritic impacts, asteroid impacts, on the surface of Mars that create depressions, craters, which show that there's water ice just under the surface, which then over time sublimates off into the Martian atmosphere. And of course, on the lower right and upper right, many, many places on Mars that clearly look like, morphologically, that water has been flowing there for some long period of time, large outflow channels from some kind of large events. Next. We think there's a big chance from the topology that Mars once had a great ocean, perhaps, inland seas, some fresh water, some salt water. And in fact, there's just an enormous amount of water probably still today frozen underneath Mars from the evidence. Next. We think maybe 500,000 years ago, because of the changing tilt of Mars, that it probably had a kind of mini ice age, and the polar caps would have expanded almost all the way to plus or minus 30 degrees. Next. Now, living on the surface of Mars is not going to be easy. There are a lot of dangers. Now, from a microbial standpoint, I think the Earth is probably the most dangerous planet for humans in the solar system. But Mars doesn't have a magnetic field, it doesn't have a thick atmosphere, and so we do have to worry about things like radiation. Next. So we have the RAD instrument, which measured the radiation next all the way to Mars, so we learned about the cruise, and it's continuing to measure that radiation level on the surface from cosmic rays, galactic cosmic rays, solar cosmic rays, so we're understanding what those risks are. Clearly a mission to Mars is going to be risky overall, but all of our space missions with humans are risky. Next. If you don't like the surface, there's places where we have access to subterranean lava tubes and where the ceiling has collapsed, and you might be able to build an encampment underneath of Mars with a big dome, maybe an inflatable, who knows, but that would be protected from that surface radiation if you were going to stay for a long time. Next. These are all the observations we're making. So what are our next steps on Mars? Next. So we have a Mars exploration program, a series of interlinked missions which help us learn more and more about Mars on each mission, and also are giving us further steps in human exploration. So we currently have the missions I told you about with Curiosity. The MAVEN spacecraft to study the Mars atmosphere and how it's lost to space is on its way to Mars. It'll be there this fall. We have participation with the European Space Agency Trace Gas Orbiter. We're preparing an InSight mission to land on Mars and study Mars' interior. In 2018, participation in the ExoMars with a Mars Organic Molecular Analyzer to look for organics. And the big news is in 2020, we're sending the next rover based on the chassis of the Mars Science Laboratory, but with new instruments and new capabilities. Next. As I said, MAVEN's going to help us understand what happened to Mars. How did it lose its thick atmosphere and all that water that we were talking about? When did it happen? So between Curiosity and MAVEN, we hope to unravel that mystery. Next. And then, of course, the Mars 2020 rover, which will have new instruments. We're in selection now, but it will extend our astrobiology search for evidence of past life, past habitable environments, but also to enable the future. In collaboration with the Human Exploration Operations Mission Directorate and Space Technology Mission Directorate, we have accommodation for a significant payload that's going to do in situ resource utilization. It's going to extract oxygen from local resources, and this will be the first demonstration of that on the surface, deliberately intended to support future human crews. Next. So Mars exploration is a common goal for all of us here at NASA. Today, we're working together at the margins, but in the future, next, we're going to be inextricably linked as we try and do human exploration, science, and develop technologies that will get us to Mars and then allow us to work and thrive on Mars. Next. So just like Neil Armstrong's footprint on the moon, we are doing wheel prints on Mars today and inspiring, young and old alike. Next. We had our astronauts. This is one of my favorite photos of the Apollo 16 crew with John Young, my hero, in the background. Loved his geology training. Next. We're training crews today and people to develop the technology, the science, the exploration techniques on planet Earth in environments that are similar to Mars, preparing the way for what we will do on Mars. And it's my great belief, next, that our future is on Mars, and this, courtesy of Photoshop, is Jack Schmidt on the moon, but what we might see, hopefully soon, in a future scientist on Mars. So with that, I'll hand it back to you, Trent.
Thanks, John. And you're able to stick around for a bit so when we break for Q&A to take some questions? Excellent. Okay, so we'll keep moving forward with the program. All right, thank you for that, John. Our next speaker is William Gerstenmaier. He is the Associate Administrator for the Human Exploration and Operations Mission Directorate, a position he's held since 2005. This makes him the official responsible for all aspects of NASA's human exploration of space. This includes, of course, the International Space Station, the development of the Space Launch System rocket and Orion spacecraft, and he provides strategic guidance and direction for the commercial crew and cargo programs, providing logistics and soon crew transportation to the International Space Station from U.S. soil. He began his career at NASA in 1977, what's now the Glenn Research Center, or was NASA Lewis, working on aeronautical research. Throughout his distinguished career, he's held multiple positions in a number of programs, including the Space Shuttle program, later the International Space Station program. Among the highlights, this includes directing the safe completion of the last 21 Space Shuttle missions that completed construction of the International Space Station, the orbiting laboratory 260 miles overhead. Please help me welcome William Gerstenmaier. Bill.
Thanks, Trent. Can I have my next slide? John gave next slide. John gave a great overview of what's going on in Mars today with the rovers, and I think it's interesting as we kind of sit here and we all look and we're inquisitively asking, was there life on Mars? I think the other question is we should be asking ourselves is, when will life be back on Mars? And each one of us in this auditorium has a chance to affect that future, to help us get humans to the surface of Mars to actually do investigations. And as John described to us, Mars is probably the most Earth or human hospitable program, or planet rather, in the solar system. So how can we take advantage of what's there on Mars, and how can we move forward? So I think the first thing we ought to talk a little bit about is why do we do human exploration? John showed a tremendous advance in our tremendous knowledge of what's occurred on Mars. If you look at what's occurred from the 60s through today, our knowledge has really advanced tremendously on Mars through robotic exploration. So I think of scientific and human exploration and pioneering as marking advancing civilizations and extending human presence. It expands our knowledge, fuels the imagination, spurs commerce, but it does require risk acceptance. The other term that I'm kind of bringing out in here that you maybe haven't seen before is I talk about pioneering. And that's brought out purposely because I believe that the amount of effort it takes to send humans to Mars shouldn't be an exploration activity. I think of exploration as you go out, you visit something, you learn something new, and you come back. I think of pioneering as we're actually making a step to move out with the intent to actually stay for an extended period of time. So I'm trying to change the rhetoric a little bit. So we talk about thinking about pioneering Mars, or going with the idea that we will stay with an extended human presence for an extended period of time and take advantage of the Earth-like properties of Mars as we move forward. I think, again, exploration and pioneering leverages really powerful motivations for us. It ignites our imaginations. It makes us think of things impossible, think of things in different ways. I mean, it leads to discovery in science and technology advances, and we'll hear again from Mike Gazarek later about the technology that's required to make these things happen. It also creates a vision of a better future for next generations. We look at what we can do with our technology and how we can keep humans alive in this environment. If you think back, many of the problems we're trying to solve in the Martian environment, we will be trying to solve here on Earth. So there's a lot of things that we learn that affect us every day today on Earth that we can learn by going to Mars. You know, and then again, as it's clearly evidenced from both what John's saying and what I'm saying, is that this exploration is really done in partnership. You know, robotics, they explore the distance hazardous environments. They extend our scientific knowledge, our understanding, our planning for the human missions that will follow. But then the human explorers, they provide greater speed, intuitive ease, and efficiency as they do the exploration. And I think you can see that again as you contrast what we did on the moon and what we're doing with the rovers on Mars today. If you look at where the human rovers have driven around on the surface of the moon compared to the distances that the robotic rovers have done, the moon exploration with the human actually there driving dramatically increases the amount of area we were able to cover. The geologist in place can actually go find interesting rocks that are there that are immediately intuitive to a human. So cutting that time delay between when the investigator or the researcher sees the data is really important, and putting the humans there. But to do that, we have to understand the environment. We need to do things like we're doing with the radiation monitor on the surface of Mars today, so we can understand what that environment is, so the risks are reasonable for us to go do these activities. And then a human space exploration really, you know, garners national prestige. It unites nations around a common goal, and there's probably no better example of that than the International Space Station and the partnership that's working and operating in space today. So again, we build on our investments in technology, robotics missions, International Space Station, commercial crew and cargo, space launch systems, and Orion. And America's poised to lead the next wave of partnerships for international science and human space exploration. I mean, if you look at all those words that are down there in that bottom little phrase, every one of them is in the Human Exploration Operations Mission Directorate. So we don't have a single program. We're really linked as an overall series of programs, all pushing human presence into the solar system. Next. This is a chart that John used. Again, I think that this is not a single directorate activity. We need to really look at the way we're working together, and I would say on this chart we probably ought to update the chart where it says future. The future is now. We are really working together with the Space Technology Mission Directorate, the Science Mission Directorate, and Human Exploration to look at ways that we can break down barriers between our directorates where we used to work as single activities, how we can combine those activities. And it really started it's been going on for a long period of time, but I think we're doing it even more now as you see the radiation monitor, and you saw on the heat shield that was used for Curiosity rover, we flew some aerodynamic probes to actually measure the Martian atmosphere to look at how we might land large objects and large cargo on the surface of Mars. Next. And it's not only a U.S. activity. This is a chart from the Global Exploration Roadmap. It's built by the U.S. and 11 other partners. It shows that there's a general consensus on what we're doing moving forward. It's not a plan, it's not a detailed investigation, but it provides a general framework of what we're interested in doing. It shows the International Space Station, which is critically important to us today. You'll hear some more about that later this afternoon. Space Station lets us understand the microgravity environment, how it affects the human. It also lets us understand how hardware performs in the microgravity environment and in the space environment. It'll let us gain knowledge about life support systems to keep humans alive. Tremendously important to what we're doing going forward. In the middle, you can see a series of robotic missions and projects, and those allow us to get prepared. You know, we're looking again internationally. It's not just one nation's robot or activity that's going to Mars. How can we put other experiments on other payloads, other planetary things to just continue to bring back knowledge? And then lastly, we talk about the missions beyond low Earth orbit. We talk about the asteroid redirect mission. You'll hear about that again today. That allows us to go into this proving ground of space, or lets us hone the skills that we need to really get prepared to go to Mars. It will be not easy going to Mars in any way, shape, or form, and we need to really prepare to do that. We do that preparation first on the space station, then we push the envelope a little bit further, look at the vicinity around the moon where we can have this asteroid redirected into this location to continue to build those skills that are necessary for us to eventually go to Mars. Next. And this is the same chart I think that Charlie used, and is basically on the scorecard. Again, you can look at it again. The low Earth orbit activity, that's the Earth-reliant place where we can get back if we need to from space station. We can bring supplies up very easily. Then we go to this proving ground to space where now it's more difficult to get to. We need to hone our skills in the proving ground to space, much like we did with Mercury and Gemini as leading up to Apollo. We build skills, we build techniques, we build operational techniques in this region. So we're really preparing ourselves with that ultimate goal towards Mars. And you know, the Mars chart is interesting. You see the 4 SLS rockets essentially being launched from the Earth heading towards Mars. You know, some folks said that it looks like we're attacking Mars. That's not really the intent. The intent is to show how complex it is, to actually put some kind of capability on Mars. You know, John showed some extremely interesting pictures. Could we take advantage of the lava tubes, et cetera, on Mars? If we put some capability down ahead of time before crews go, how do we do that? And we need this heavy lift launch vehicle on the order of 4 or 5 heavy lift launch vehicles to actually get that infrastructure in place for humans to go there, to reside for a period of time and then come back. So again, I think you can look at this as an expanding presence. We can continue to make significant progress. I think you'll hear later today how all these pieces really link together. So they appear disconnected. They appear that they're not really linked, but they truly are linked. Commercial crew, commercial cargo is extremely important in low Earth orbit. It relieves us of the burden to take supplies to station. It allows us to get cargo to station without us having to build new systems and develop systems. Those are available from commercial industry. Space station lets us work internationally with our partners. It lets us build these skills for the human side, provides direct benefits to us here on the Earth, lets us experiment with technology. The asteroid redirect mission places us in cislunar space where we're now 4 or 5 days away. It increases the risk environment, requires us to do now automated rendezvous without communications back to the Earth potentially, pushes us on the other side of the moon where we start having periods of no communication with the ground, starts breaking that tie with the Earth, lets us get skilled and ready to go do that next step, which is Mars ready or Earth independent, when we're really ready to break that tie with the home planet and move out to Mars. So it should be interesting as you listen to all the groups today and think of how you can be part of this activity and how you can contribute to putting human presence on Mars. So thanks.
Are you able to stick around a couple of minutes to take questions here? Great. We'll break for Q&A right after this panel. Before we do that, let me ask our panelists to begin to come up and take their seats, if you would. Great. Just a quick reminder, we'll break for Q&A directly after this panel. You're going to see a number of presentations today. You've seen quite a few excellent ones already. Those will be archived later at nasa.gov/exploration. If you have questions for us, for any of the speakers so far, you can ask us those questions on Twitter using the hashtag AskNASA. Of course, you can find out more information about NASA's exploration plans at nasa.gov/exploration. And again, the hashtag for today is Mars if you're joining online. It's my pleasure to introduce our next distinguished panel, representing different offices and divisions in the Human Exploration and Operations Mission Directorate here in Washington. They're here to talk to us a little bit about the portfolio of Human Exploration and Operations, or what we call HEO, and how it relates to the ultimate goal of sending humans to Mars. To my left is Sam Shamimi. He is the Director for the International Space Station here at NASA headquarters. He has 27 years of experience in human spaceflight, Earth, and space science missions. His background spans development of complex space systems, testing in extreme conditions, and real-time crew operations. He's been employed at 4 different NASA centers: Johnson Space Center in Houston, Ames, of course, in California, Goddard Space Flight Center right down the road here in Greenbelt, and here at NASA headquarters. He's also been a part of many programs here at NASA, including the Space Shuttle and International Space Station programs. Next to Sam is Phil McAllister. Phil is the director of the Commercial Spaceflight Division here at NASA. He has more than 20 years of experience in civil, military, and commercial space programs. He currently oversees management of NASA's commercial crew and cargo programs. Throughout his career, he's participated in the development of new launch vehicles, rockets, the redesign of the International Space Station, and the advancement of several commercial space ventures. Next to Phil is Dan Dumbacher. Dan is the Deputy Associate Administrator for Exploration Systems Development. Dan has more than 30 years at NASA. I'm sorry to say he recently announced he is retiring. Going to embarrass him here for a second, to return to his alma mater at Purdue. It's very much our loss, but I'm really happy he was able to join us today and talk about the work he's been managing on the Space Launch System rocket and Orion spacecraft that will carry humans farther into space than ever before, including to Mars. Next to Dan is Michelle Gates, Senior Technical Advisor for HEO. She has more than 20 years of experience at NASA. In this role, she provides overall advice and support to Mr. Gerstenmaier, our Associate Administrator, across a broad array of strategic and tactical issues affecting the Mission Directorate. She provided critical support to the implementation of a flexible, sustainable human spaceflight program portfolio. You'll hear more about that, including both government and commercially owned operated elements during the transition from the Space Shuttle program. She also represents the Directorate in cross-cutting agency initiatives, which includes, most recently, the Asteroid redirect mission. Finally, we have Jason Cruzan, who's the Director of the Advanced Exploration Systems Division. In this capacity, Jason oversees AES's portfolio, which pioneers new approaches for rapidly developing prototype systems, demonstrating key capabilities, and validating operational concepts for future human missions beyond low Earth orbit. Those are complicated words. Basically, if it looks like sci-fi, it's really cool and long lead. It's probably Jason working on it. So with that, I will hand it over to Sam.
Thank you, Trent. Could I have my first slide? All right, I'm going to follow up where Gerst and John and Charlie left off, talking about space station and how we're utilizing space station to get us beyond low Earth orbit. Next slide. As Charlie mentioned, station has, we've agreed to extend it for at least another 10 years, and what we're doing on station is directly linked to deep space human space flight beyond low Earth orbit, and to the development of the commercial low Earth orbit market for all the capabilities that we use in human space flight. Next slide. You've seen this before from Mr. Gerstenmaier. I want to focus on a little bit on what space station is. If you look down at the bottom of that slide and look at the time periods that we are actually spending in space. On space station, we have 6-month duration crew expeditions. Next year, about this time, we will start our first 1-year expedition cruise. And the systems that's needed to keep crews alive, where it shows Earth reliant, I'll show you, we are really Earth reliant. And when you get out to the Mars time frame in the 2030s, our missions are 2 to 3 years in length to keep crews alive. So it's a large gap between where we are today with space station and human spaceflight and where we needed to go for Mars. Next slide. So this is sort of a graphic. If you look at the bottom caption there, we're basically car camping in space right now. Everything that we need to keep crews alive in space is very close by. Round trip times to space station is within 2 days. Our communications is near real time. You might as well just be on a phone. We have crew exchanges 4 times a year. We have up to 15 flights to space station with crews and supplies. And we also get all our medical samples and atmospheric samples and our research samples that come back to the Earth. When we go to Mars, these things really don't exist. We also have a convenient way to get rid of trash. We can take trash off of space station, put it in our commercial vehicles, and then burn them up in orbit. If you go to the next slide, going to Mars, we have none of that. In fact, our communications are quite delayed. It can be up to 42 minutes round trip communications time. So to go from where we are on station to go to where we for Mars missions, there's quite a large gap in what we need to learn, and that's what the space station is all about. Next slide. So what station's doing to fill in the gap? So we intend to demonstrate the actual environmental control system that will take us to Mars and demonstrate it on station, based on what we're doing today right now with our ECLIS system. In our carbon dioxide removal system, we're learning what technologies work, which don't work. Same thing with our our oxygen generation and waste management systems. We're learning how the humans interact with these systems. When you bring humans, you also bring all the microbiology along with the humans and all the interactions with stuff growing inside the space station into the systems. So learning how to deal with that. We're learning how all the human health and performance activities in space to keep the crews alive for long durations, from bone loss and muscle loss to intracranial pressure in the eyes issues, and be able to keep exercise equipment going long enough to keep the crews healthy and such. We're also learning how to break the bonds of Earth through logistics and crew health and monitoring and ground to crew communications. We're doing simulations on how to do comm delays, learning how to handle logistics in a more efficient manner. We're also demonstrating all the other technologies needed to go beyond low Earth orbit, like next generation solar arrays, rendezvous sensors, and docking systems and the like. Next slide. You'll see these charts a little bit later, but I wanted to highlight on station what we're doing in the Earth Reliant and Blue section. If you look at all for this slide and the next slide, don't go there yet, but working in space, all the things for instance, communication with the Earth, our EVA capabilities, mobility and robotics, in situ utilization. We're doing a lot of things on space station and research and technology development to support those activities. Same thing with the next slide, staying healthy. Our HRP program and other programs we have on station is really geared towards keeping our crews healthy and productive in orbit. Next slide. So what we're doing on space station is not only related to deep space exploration, but it's also related to the development of low Earth orbit commercialization of a market-driven activity. All the things we need to keep crews in space for long durations is also the same things we need to keep crews safe in low Earth orbit. Things like habitation structures, ECLIS systems, crew health and monitoring, things like medical equipment, exercise equipment, EVA support systems, spacecraft systems like avionics and electrical power, and things like cargo supply and crew supply. All those things we're actually working out on space station that will enable both exploration of Mars and the development of the low orbit commercial market. And next slide, and I believe that's all I've got. Do I have time?
Thanks, Sam.
Do I have
Phil.
time for questions?
Well, we'll break as soon as the panel's
Okay.
over. We'll take 10 to 15 minutes as time allows to take questions. Go ahead, Phil.
So thanks, Trent. I'm here to talk about our commercial spaceflight initiatives at NASA and really demonstrate that this is an integrated strategy for NASA. Our commercial spaceflight initiatives are really enabling NASA and the nation to do much more. What we're finding is that NASA doesn't need to do everything. We can rely on the private sector now to just purchase services for NASA. And the reason why that's good is if NASA had to do everything, we would always be limited by NASA's budget for our aspirations in space. And once we bring the private sector along, the pie just grows bigger, and the nation can do more. We can all do more when we have the combination and the partnerships between the government and the private sector to push the boundaries of exploration out into the solar system. So next slide, please. What I like about this shows our cargo demonstration project that was completed in 2013. And what I like about this is all actual pictures. There's no artist conceptions on this. We made it all the way through development with 2 new launch vehicles, 2 autonomous spacecraft, 2 end-to-end systems capable of supplying the International Space Station and cargo to low Earth orbit, and 2 privately developed launch sites as well, all in the span of about 7 years. We went 4 for 4 in terms of launches and 2 for 2 in terms of berthings, and now we've already seen regular cargo delivery to the International Space Station. two missions for SpaceX, one for orbital sciences. Actually, a Dragon is on orbit as we speak, and the next launch of an orbital sciences Cygnus is in the June timeframe. So we're seeing that transition already. NASA facilitated the development, but private sector very much took the reins for the development. They own and operate these systems. NASA was an investor and a technical advisor throughout this process, and now we're a customer, just purchasing services. We don't own and operate these systems, and it really frees up NASA to do the more difficult jobs of deep space exploration, which Dan will talk about. Next slide, please. So to follow on the footsteps of commercial cargo, we are now in the midst of commercial crew. You can see there's a mix of real pictures and some artist conceptions, which shows we're about halfway through development. I've got another slide which will show you where we are in the overall roadmap. We have 4 partners today that we are interacting with to help provide eventual crew transportation services to low Earth orbit and the International Space Station. 3 of those partners, Boeing, Sierra Nevada, and SpaceX, are funded, meaning we are providing not only technical expertise but also investment. Blue Origin is on a no exchange of funds basis. But what I really like about this slide is it really shows the diversity of approaches. We have different levels of reusability, different rockets, different designs. Shows multiple different ways that we can do this, and it really strengthens this whole approach and process to bringing crew to low Earth orbit. We don't want to be reliant on a single system. That can be a very tenuous situation, and we now are seeing multiple designs. These companies are very capable of doing this mission with NASA's help, and hopefully we will be seeing the fruits of their labor fairly soon. Next slide. So this is our roadmap chart. You can see that we started in about 2010. We're slightly more than halfway through the development, so we're transitioning from a lot of design reviews to more hardware testing. So you saw on the previous slide a lot of parachute tests, some drop tests. We're seeing some actual hardware, so it's getting very exciting and getting very interesting. We have a lot of work ahead of us. We are about to make awards for the next round, which you can see we call TCAP, Commercial Crew Transportation Capability, later on this summer, which will take us all the way through development and complete. Hopefully I'll be showing a similar picture to cargo, which will show our crew transportation systems in just a few years' time, hopefully. Next slide. And then one other thing that we wanted to leverage, we've noticed that there was a significant number of companies that were popping up with entrepreneurial ideas that wanted to provide commercial services to not only NASA but to commercial customers as well, non-NASA customers. This is good for NASA. Again, it's good for private industry. It's good for the nation. So we have a lot of expertise at NASA that we wanted to share and make available to these companies to hopefully increase the likelihood that they will be successful so that we can purchase services from them, just like we're doing with COTS now, later on. So we are in the midst of an evaluation right now. This is a no exchange of funds. Space Act agreements is what we'll feature. So each company, each partner, the government and the private sector, will bear their own costs. And we collaborate, which is why we got the title, Collaborations, through this partnership, and we hope to find and be able to facilitate additional services, not just crew and cargo, but other services that NASA can leverage in the future. We hope to be making selections in the July timeframe for multiple unfunded Space Act agreements. And so with that, what I'd like to say is that we're seeing a very logical progression, in my opinion, of pushing the boundaries out into space, where the government is doing those things where you really don't see a clear profit motive. There might only be one customer, that we're really pushing the state of the art in terms of our deep space initiatives. And then we see the private sector coming in behind where you can actually see a profit motive. These missions are a little bit more achievable, and it is time now, it's certainly for low Earth orbit, for us to move that responsibility over to the private sector. They've demonstrated capability, and then that frees NASA up to do the state-of-the-art things, the pushing the state-of-the-art things that are still very, very difficult. And through this integrated strategy, I think you're going to see us go a lot further and a lot faster. Thank you.
Thanks, Phil. On to Dan.
Okay, thank you, Phil, and welcome again, everyone, both here in person as well as online. If we could go to the next chart, please. What we'd like to do is talk about the progress that's been made on the Space Launch System and Orion since the 2011 timeframe. These programs are real. We are making good, steady progress on these programs. And even though there are some artist concepts in this montage here, you see some of the testing that we've done with the parachutes, technicians working on building the hardware, changes at the Kennedy Space Center for the ground systems, all in preparation to go achieve the goals that John and Gerst have talked about in terms of getting humans to Mars and continuing our exploration into deep space. If we could go to the next chart, please. This is a picture of the Orion spacecraft currently at the Kennedy Space Center being prepared for the flight test in December of this year. This flight test, we'll talk a little bit later, but the main purpose is to test out the heat shield and some of the structure elements of the Orion spacecraft so that we can use that information to better design the spacecraft as we prepare to take humans further into space than they've ever been before. On the left-hand side, you see some of the work with our heat shield protection, our service module, and on the right is the crew module getting prepared for its flight test as it goes through some of its final test and checkout at the Kennedy Space Center. Next chart, please. For the Space Launch System, major progress on that front also. In the upper left-hand corner, you see the domes that we are building at the Michoud Assembly Facility near New Orleans, where we used to make the external tanks, and we have totally redone the facility, put in the new tooling that we need for the friction stir welding that we use on this system, and we have tested out all of our welds so far, and all have come in clean. And on the right-hand side, you see the last tool that we are putting in where we will begin to stack the tanks and then do the circumferential welds we need to build the entire tanks. You get a feeling for the size of the structure. This is big structure. This will be the largest friction stir weld machine in the world when we complete it. All of this is on track. We will be doing our first welds in this new tool later this summer. The Space Launch System is continuing towards its critical design review. The design and the production Pathfinder work is proceeding very well. Next chart, please. And at the Kennedy Space Center, the mobile launch platform, we have repurposed it from the Constellation days, turned it over into what we need for the Space Launch System, beefing it up, getting our ground command and control software systems all in place, as well as the vertical assembly building that we will use to stack the launch vehicle and to stack Orion on the launch vehicle. So you see that's an artist concept over in the VAB that we're doing, but we have all the work under contract. The Space Launch System's under contract, Orion's under contract, so very good progress. So to give you a little bit better feel of the progress, if we could go to the next chart, which is actually the video, if we could roll the videotape, please. I always wanted to say that. Never got on the news, but I always wanted to say, roll the video. see with that, the NASA industry team across the country is making great progress, and you'll see it first step with our Exploration Flight Test 1 this December. We will do 2 high Earth orbits. Orion will re-enter the Earth's atmosphere at approximately 85% of what we expect the re-entry velocity to be from the Moon. So we will get a very good test and put that data directly into our design process for the next mission, if I go to the next chart, please, which is Exploration Mission 1. Currently scheduled for fiscal year 18, where SLS and Orion will fly together. We will take Orion out to the Moon, put it in a distant retrograde orbit, and this is essentially a practice mission in an uncrewed fashion as we prepare for our asteroid redirect mission. The next chart, please, will show EM Exploration Mission 2, which will be our first crewed flight of Orion, and that flight will take us out to high lunar orbit, so that we can exercise the crew systems, check out our Orion spacecraft along with the Space Launch System, all in preparation for taking crew out to the asteroid. And what we will do, what you see here is the hardware, and in addition to our commercial cargo capabilities and what Phil's team have been working on to get the transportation system in place to space station, we are extending that transportation system out into deep space. And our first test for that, will be what Michelle talks about in our asteroid redirect mission, and it's our first step on the way to Mars. Thank you.
Thanks, Dan. On to Michelle.
Dan always gets the applause for the video, which is always hard to go after. Hi, I'm Michelle. It's great to be here today. First slide, please. The next one. Thanks. So today I'm going to talk a little bit about the asteroid redirect mission, which is a compelling early mission in the proving ground that Mr. Gerstenmaier and Sam talked about earlier. The asteroid redirect mission will utilize advanced capabilities and technologies that are needed for the future human exploration of Mars, as well as complement the International Space Station learning and experience that Sam described earlier. Next slide. The asteroid redirect mission consists of 3 segments. The first is actually a benefit of the Science Mission Directorate's Near-Earth Object Observation Program, in which we'll identify target asteroids that actually has already begun, followed by the demonstration of an advanced solar electric propulsion system to redirect an asteroid to a stable orbit in the lunar vicinity. And finally, the crewed mission to take our astronauts aboard the Orion and SLS vehicles to visit, explore, and take samples from that asteroid in the stable orbit around the Moon. Next slide. The asteroid redirect mission, or ARM, integrates several building blocks as we initiate deep space human exploration, including, again, the Orion multipurpose crewed vehicle, the Space Launch System, Heavy Lift Launch Vehicle, Advanced High Power, Long Life Solar Electric Propulsion Technology Components and Systems, the capture and maneuver of non-cooperative targets, the moving of large objects through interplanetary space trajectories using solar electric propulsion, and the integrated robotic and human vehicle stack operations in deep space. You'll find this mission significantly contributes to the extension of human exploration beyond low Earth orbit and into deep space. In fact, we'll go 1,000 times farther than LEO for the first time in 40 years and for longer duration in deep space than humans have been before. Next slide. Just a few of the assets that are being enhanced by the Science Mission Directorate for detection of potentially hazardous objects, which the asteroid redirect mission is benefiting from, including enhancements and upgrades to the Catalina Sky Survey, full-time operations on Pan-STARRS 1, completion of actually a Pan-STARRS 2 asset, the space-based observation of asteroids using the WISE telescope, and some enhancements to radar and other assets. Next slide. There are 2 capture options which are currently being investigated for the Asteroid Redirect mission, Robotic mission, which actually the concept has been pretty fleshed out. If you had seen the opportunities for them in March, it's available online. The first option is the inflatable capture of a small free-floating asteroid. We are estimating it would be less than 1,000 metric tons in mass, which is actually still pretty large. The current reference target is 2009 BD, which would be crew accessible in the lunar distant retrograde orbit by February 2024, potentially as early as 2023, depending on trajectories. And actually a recent Spitzer observation of 2011 MD is likely to raise that to a valid target as well, and that would be crew accessible as early as August 2025. Option B is the robotic acquisition of a 2 to 4 meter boulder from a larger asteroid. And actually, while there, we would do a deflection demonstration of that larger asteroid to demonstrate planetary defense techniques. But regardless, with either option, there would be a large asteroid mass made available in a stable orbit around the moon for exploration and sampling by astronauts. Next slide. And indeed, this crewed mission is quite compelling for the mid-2020s to complement our work on the International Space Station. The astronaut crews would launch aboard the Orion multipurpose crewed vehicle and the SLS heavy lift launch vehicle, traverse the 8 or so days out to the lunar distant retrograde orbit using a lunar gravity assist. There, the Orion vehicle would rendezvous and dock with the high-powered SEP spacecraft with the asteroid attached. You see the integrated robotic and human vehicle stack there at the top right on my side corner. And there we would actually demonstrate integrated attitude control, including solar orientation, EVA, support capability in deep space trajectories, which is still fairly close to the Earth and again the proving ground. That trajectory is an estimated 11 days return from the moon, or from the lunar orbit, sorry, counting a total of 26-day mission, returning the samples with the crew to Earth. Next slide. So we've done quite a bit of work as well in investigating the potential and better understanding the applicability of this high-powered solar electric propulsion system to enable future human missions to Mars. And it turns out that there are several architectures and opportunities which are going to be described, summarized by Jason next. However, the solar arrays, the component technologies, potentially the spacecraft bus would be exactly the same bus that could be used to take cargo to Mars. The exploration EVA capabilities described earlier, including solar orientation, sampling, the portable life support system, which is actually a primary life support system, as well as the rendezvous and docking sensors, which we're looking to enhance and exploit commonality there as well. Thank you very much.
Thanks, Michelle. Senator Ryan. And on to Jason.
Great. I'm going to be batting cleanup a little bit on this panel here. So what I'm going to try to do is step back a little bit higher level back to some of our architecture planning and work we've been doing there. If I can get the next slide, please. One of the first things we've talked about is as you look at how to bring together all these various elements within human spaceflight, space technology, and science, you need to be driven by a couple key principles in order to drive all of our what would seem to be separate programs into an integrated effort. These are the 6 guiding principles that we've been using to drive that. You'll see slight variations of these that we actually are constantly evolving it as we've been actually getting feedback from you and the community and our stakeholders. The first of which on the list here is living within our budget realities, and in the near term executing with our current budgets, and in the long term looking at growth that's commensurate to economic growth. So not looking at very historic views of very large increases to the agency that are all spiked and not very level level set as we go to execute all these programs. We're also looking at the application of high technology readiness levels. So you're looking at that with what Michelle described with our ARM mission is using a series of technologies stitched together in a very compelling way to advance those capabilities. And that's due in part because of the high readiness levels that they are. At the same time, we're though going to keep a balanced portfolio of next generation technologies to help advance our stepping stone approach on the way to Mars. The next piece here is near-term missions. So one of the things to think about is this isn't just a monolithic program that one day we launch a singular campaign to Mars, but rather it's a series of missions over time that have a constant cadence for allowing us to advance our capabilities in a very systematic way that go from precursors to pre-emplacement to enabling then our crew, first crew visit to Mars and Mars vicinity with that. Along with that, you heard from Phil and also from Sam related to commercial business. We are expanding the use of commercial models and commercial acquisition of capabilities as we keep on pushing the envelope and capabilities. Where is the next market that kind of follows behind with us in order to enable us to acquire capabilities at a lower cost for us? Michelle touched on it a little bit. One of our key principles is multi-use evolvable space infrastructure. So when you look at the components of ARM, the Asteroid Redirect mission, you're looking at solar electric propulsion that at a modular level is our evolvable strategy for solar electric propulsion for cargo to Mars. You're looking at reuse infrastructure of Orion and SLS as core principles of our work that we have. And the last one is building on our international and commercial participation. So we have a strong relationship with our space station, International Space Station community, but in addition to that, our global exploration roadmap countries as well. And we want to build upon those partnerships to not go it alone, but to go together and answer a lot of the key attributes that we need to send crew before we send crew, answer those attributes as a global community, not just as NASA. So the next slide. So I'm going to take a little bit of time to explain this chart because we haven't briefed this one in public all that much at this point. So in the past, you've seen NASA's plans for Mars to be very monolithic in nature, meaning that we have a series of build-outs and we have a singular mission that sends humans to the surface of Mars. What you're seeing here is a shift in our general philosophy to an Evolvable Mars campaign. So what we're looking at is what are the various capabilities that you don't just build a whole series of hardware and launch at once, but rather over a period of time, start pre-emplacement of capabilities and testing those capabilities, not just for the purpose of demoing it, but to actually, if it works, it now will be in place for future missions. So we're looking at the various trade spaces that you see. Solar electric propulsion as our in-space propulsion segment that we have. We're studying the use of in-situ resource utilization. All of our Mars architectures require some level of ISRU to be able to live off the land and go to what Mr. Gerstenmaier said about pioneering and starting to figure out how do we harvest resources and consumables, whether it's for human consumption or for our rocket engines consumption, how do we harvest those along the way? Thinking about, as we have been already with our Mars Science Lab, you heard about the RAD instrument, our previous entry, descent, landing technologies with that. Mars 2020 is extending that. But how do all these robotic precursors with us and the Science Mission Director work together to answer key strategic knowledge gaps we have about the stepping stones as humans extend into deep space? So we're looking at this, how humans or robotics actually work together and complement each other, that then precursors actually evolve into what is more like pre-emplacement of hardware for, say, in-situ resource utilization plant or pre-emplacement of habitats that are extensible for our future human returns. So we're doing various trade studies related to that in cislunar space and extending that into Mars orbit. We're looking at various other stepping stones that may include Mars moons or a direct path to Mars surface and how those can help weigh in on our overall campaign to Mars. So this is a really critical way to start thinking about human exploration, not as a singular monolithic effort, but rather an integrated effort across all of NASA and all of human spaceflight. So next chart. We're doing this because fundamentally Mars is extremely hard. at the end of the day, we need the critical transportation elements both to get to and from space and into deep space. We need the in-space transportation, both propulsion and the habitat that we have there. We obviously, the happy and healthy piece. We need to be able to figure out the high reliability systems that Sam alluded to. How do we build off a station experience but increase the reliability and decrease the consumables for us sending the crews all the way to Mars? And at the end of the day, when we get there, and getting there is over these multiple missions, how do we ensure that we're well equipped and productive over that time? So how do we look at the science aspects that can be addressed both in precursor missions but then as we send the crew there? So next slide. So a couple folks started talking about this, Sam did at the beginning. So we've been breaking down our various elements into 3 categories. The first is which is transportation. So if you look at transportation, fundamentally it's the crew transport, it's cargo, it's propulsion, and it's planetary rendezvous and ops and landings type capabilities. And what you're seeing here is an integration between our early flights of SLS and Orion and the Asteroid mission starting to buy down the risk and the proving on related to crew transportation and cargo. In addition to that, the solar electric propulsion then starts bringing down our risks and bringing up our capability as a knowledge for in-space propulsion for pre and placement of some of that cargo. Michelle touched on the fact that manipulating large objects such as asteroids start actually working out the fundamental dynamics to be able to do trajectories of large stacks to and from Mars. Do we throw away everything on every trip to Mars, or do we rather actually put it in different parking orbits so that we use it on the next visit to Mars? So we're looking at how do you maintain orbits in long periods of time and manipulate those objects that we have. In addition, we look at opportunistic partnerships with our international commercial opportunities related to can we advance in situ resource utilization knowledge even in the cislunar space as our international partners focus on those areas. Next chart. One of the key points that a lot of others have brought up is we're continuing a strong partnership between us, science, and space technology. Mars 2020 is a continuation of a path of cooperation within the agency, building on our knowledge and gaining knowledge in entry, descent, and landing with another flight of our Medley instrument on Mars 2020. And as John noted, addressing strategic knowledge gaps, one of which is in situ resource utilization, which is our key to us on our return from Mars. One of our fundamentals in most Mars architectures is the production of oxidizer for our propulsion systems for the ascent vehicles and our return trip on the surface of Mars. So Mars 2020 is beginning that buy down of the knowledge of that we need before sending humans. Next slide. In addition to that, we're trying to also work with the commercial sector on landing capabilities. So we have an initiative called the Lunar Catalyst, which very much like Phil described, we're doing no exchange fund partnerships with commercial industry. This allows us to continue to advance our landing capabilities that we've been advancing internally on programs such as Mighty Eagle and Morpheus, but also then bring in the commercial sector as well to continue to advance this for our use for planning on Mars, but also for commercial use as they endeavor to create landing type services and landing capabilities for the lunar area. In fact, we're getting ready to announce the selection of this very, very soon, most likely this week. So we're looking forward to the announcements of these partnerships that we have here. Next one. One of the things to pull on is as we advance commercial capabilities, like in Catalyst, it allows us to start testing ISRU technologies maybe on a more periodic basis. So one of the areas of working in space, you'll see ISRU is captured in the proving ground down here, but you'll also see the communication challenges, the spacewalk challenges. During assembly of space station, we overcame a very big challenge of rapid EVA, more frequent EVA, and as we go to the Mars surface, now we need to actually pick up that same capability but in deep space, and actually get even more rapid EVA than we do on station today as we get to a planetary surface type EVA community capability. On the next one, we're going to talk about staying healthy. And as we do these high reliability type missions in the proving ground period, we are going to have to figure out how to not, as Sam and others pointed out, how not to do grab samples for atmospheric monitoring, how to do remote medicine. We are days from home at that point. and even longer duration as we step even further out from cislunar space. So how do we do that? We also look at advancing of automation. So we're utilizing space station today on looking at more and more systems that we can automate and make things crew-tended and less attentive to the ground and have less interactions with the ground so that the vehicle can save itself when we're on these longer duration missions. I already touched on environmental monitoring, but how do we do that in a more closed loop, Earth independent type phase where you can't bring samples back to Earth and run the test here to ensure that the quality of the atmosphere, or when we get to the surface of Mars, that the actual Mars environment hasn't actually done something to our atmosphere where our crew is living and working there. So that what I'm trying to show you here is that we're moving away from this monolithic kind of program strategy to more of this evolvable campaign where every contribution that the agency is putting in allows us to answer these key strategic knowledge gaps and enable us to get to Mars in a very productive and efficient way over a period of time. So with that, I have my last slide, and I'll leave that up for whatever Q&A we have time for.
Thank you very much. Please help me thank our panel, and we'll take a few questions. All right. So we have a couple of microphones in the audience, so we'll take a show of hands and get to some of those, and then we'll take some of the questions from social media, but we'll start down here in the front with Ken. Go ahead.
Hi, thank you. Ken Kramer for Universe Today. Thanks for doing this today. I have a question for Bill and John, and maybe the others too. For Bill, can you describe a little bit? You've talked a little bit about EM1 and EM2 and getting to Mars, but there's not a lot in between. Can you discuss after we do the asteroid redirect, what comes beyond that before we get to Mars? And for John, can you talk a little bit about the radiation risk? You're an astronaut. You guys have talked about having to relax the radiation requirements. You're going to have to accept a higher chance of radiation damage to your bodies. Can you talk about that from what is going to be acceptable and what is acceptable to the astronauts? Thank you.
First of all, to answer your question a little bit about what do we do after the asteroid redirect mission. We really talk about it as a proving ground of space. So we think we need to do much more than just one mission in this environment. I think the asteroid in itself will be compelling in the fact that once it's there, it's now available as a resource to be used. As Jason's talked about, we need to look at in situ resource utilization. Potentially, we look at putting a habitation module, a crew-tended habitation module in the same distant retrograde orbit around the moon. And what that's doing is, again, that habitation module would play a role in the Mars mission, potentially the habitation module for the Mars mission that comes forward. So what you see is essentially a cadence of things that we're doing that all are focused on Mars, but how do we buy down the risk associated with Mars? How do we gain the experience, gain the technology, gain the hardware experience, and the operational capabilities to keep moving? So we see, roughly a cadence of flights after this EM2 flight or after the asteroid redirect mission that will continue to build on those. It's also important that if the asteroid isn't there for EM2, we would still plan on flying EM2 in roughly the same time frame, in the 2021 time frame. When the asteroid is there, say it's one of the candidates that Michelle talked about, it could be in the 2025 time frame, and then we take Orion to that point. So again, we kind of let our cadence and experience drive what we go do and what we move forward. We also let our risk tolerance kind of drive what we want to go do. Dan laid out a very interesting mission for EM2. Maybe it's after we see EM1, we may determine it's too risky to go into a distant retrograde orbit. We want to do some kind of more of a lunar flyby. We need to be adaptable and don't say that we've changed a program or we've fallen off the program. We need to create a framework and a structure that allows us to take data, maximize our learning, and if we learn something that moves us in a different direction, we need to be nimble enough to move in that different direction. So that's how this whole kind of framework all gets laid together into essentially this architecture we talk about to eventually get us to Mars. John?
Sure. Well, Ken, you've asked a really important question, which is about the radiation risks. And that's something that we're learning about with our RAD instrument on Mars and Cruise to Mars that we'll learn about on future missions, but we're also learning about on the International Space Station. Now, we're lucky here on Earth and in low Earth orbit to be protected by the Earth's magnetic field and on Earth by the atmosphere, although there's a pretty high natural radiation environment which we evolved in. And so the body has mechanisms for repair of cells and program cell death when there's radiation damage for the low level of radiations that we live now. We really don't know what's going to happen as we go out into deep space. We're exposed to the galactic cosmic rays, which are a harder source of radiation. And so in the proving ground, that's one of the things we're going to learn about. Now, that's saying, yeah, we're going to put people out to be guinea pigs. And as a guinea pig myself for low Earth orbit flights, that's what it's about, to be human, to learn to explore, to learn to pioneer. In the same time frame, in the 2020s and 2030s, we will also be able to take advantage of really incredible medical advances where we are learning at the micro level, the nano level, how to identify cancerous cells, for instance, and how to co-opt, for instance, the actual genetic mechanisms in the cell to program that particular cell to die. There's a lot of work going on around the country at universities, at National Institutes of Health and elsewhere to help people on Earth that, one, we may learn from our space exposure, but two, what we'll learn from improving human health on Earth to apply to space exposure. So all of that work is in front of us. We know it's a risk, but on the scale of the overall risk of a mission to Mars, the radiation risk is just one of those risks. Anybody who watches a space launch or watches a human space flight launch, such as a space shuttle, knows there's a lot of energy involved. So just getting to Earth orbit, for starters, is risky. Then the cruise to Mars will be risky. Entry through the Mars atmosphere and landing, entry, descent, and landing. For the Curiosity rover, it was 7 minutes of terror. That's how we describe it. It was a risky maneuver. So we'll have to look at the overall risk. As a risk taker versus a risk manager, I can just say I think that risk would be worth it.
Let's go next to Frank Mooring here in the front. But can I also see a show of hands just so we know how to, others here in the front. Okay, so here at the bottom middle.
Hi, it's Frank Mooring with Aviation Week. For Jason, I guess, and maybe for Bill Gerstenmaier, I was interested in what you said about the ISRU on 2020 rover and then later in cislunar. Could you go into a little more detail about what you're going to do on the rover, what you might be able to do in cislunar later on, and then also how it, maybe for Gerst, how it would fit into the architecture?
Yeah, so for Mars 2020, we're looking at the production and separation of oxygen from CO2 is the fundamental. So going back to one of the things that we need for future ascent vehicles off the surface of the Mars, a good mass fraction of your vehicle to take back off the surface is your oxidizer. So we're looking at the oxygen specifically and separating that from the atmosphere of Mars. We're also looking at, as Bill noted, related to the asteroid and/or on a lunar surface, are there ways to harvest material that could be beneficial for human spaceflight? And we haven't finished those trades. I mean, some of it, if we happen to have an asteroid that has water content or hydrogen in a generic sense, could that help us with shielding and answering the radiation question? Could it serve as a point of gathering material for propulsion systems or even other consumables that we have for human spaceflight? And top opportunities with the asteroid and/or the lunar surface may be driven more by our international partners. As they return and do trips to the moon, it will give us opportunities to fly instrumentation on a more frequent basis than just flights to Mars to advance that same ISRU capability on a regular cadence with the right return on investment working with partners.
And the only thing I would add is, again, from a big picture standpoint, is we're looking at in situ resource utilization very early in this sequence because it has a dramatic change in the way we do business about whether we can use a propellant, as Jason talked about, or use the, do we can we generate propellant on Mars for the return flight? What can we use from the moon? How easy is it to do this? How effective the systems are? What kind of return we can get? Those are really important things that once we know the answers to those, they can dramatically affect the architecture and affect the mission scenarios that we put together in the future. So we've kind of structured the things we're looking at is we want to look at those things that have the biggest lever or have the biggest potential of changing the way we go forward, look at those early so we can adapt those and then change our strategy as we move forward.
Just a reminder to those watching online, we'd love to get your questions. We'll turn to them in a second. Just let us know if you have a question on Twitter using the hashtag AskNASA. Let's go to Miriam Kramer.
Yeah, Miriam Kramer with Space.com. I think this question is probably for Michelle or Jason, and I'm curious, is there a set time frame for when you need to decide the mission profile for the asteroid redirect mission? And within that, I mean, when would the spacecraft, the robotic spacecraft, need to be built for humans to be able to get there by 2025?
So the current plan is to down select between the two capture options, the one with the small free-floating asteroid and the large asteroid with the coherent mass, the boulder. We're planning for that in mid-December. Of course, it depends on what we learn. Until then, we've got the BAA out and we've got internal risk reduction going on. So we're planning for that piece in mid-December. That will segregate the class of asteroid targets that we're looking at. And our plan is to keep the final target selection open as long as possible, ideally up to a year before launch, if possible. The current plan is also for a mid to late 2019 launch of the robotic mission for return of the target asteroid as early as 2023, but most of our current potential candidates return and are available in the DRO for the crew, which means it's settled in the DRO in 2024, 2025. Thanks.
Let me just take podium privilege here for folks watching. What's the DRO?
Sorry, the Lunar Distant Retrograde Orbit.
And can you or Jason say a couple more words just about BAA, where things currently stand and what the timeline is? Because that's a unique opportunity for others, not NASA, to participate in advancing some of the technologies you're looking for.
Proposals are due May 5th.
Okay. And for more information on the broad agency announcement, the BAA, nasa.gov/asteroid initiative, I believe.
Asteroid Redirect Mission BAA is what it's called.
Right.
You can find it online.
Exactly. Okay, thanks. Let's go to social. What do we have, Lauren?
We have a lot of engineering questions coming in from Twitter here, so I'm going to try to start with some of those. First question, and this may be for Dan, from Carl Murray. Why does Orion look a lot like Apollo?
Well, that's pretty simple. Physics hasn't changed since the Apollo era, not that I'm aware of. The real issue is when we come back, when we look at the overall mission trades, weight is very important. And you have to look at how you're going to get the crew home safely. What we know is essentially a ballistic reentry is easier to do. It has its own challenges, but it's better to do it that way on a mission out to the moon and beyond because of the reentry velocities, so that we don't have to carry a winged surface all the way out and all the way back. So it becomes a mass trade, a reliability trade, and a performance trade. We have grown Orion. Apollo was designed for 3 crew. We are designing Orion for 4 to 6 crew, so it is bigger. And we have to eventually prepare it for the reentry velocities that we will need for a Mars reentry, which are faster and more energetic than a lunar reentry. So basically the physics is dictating it as we go through all the system trades.
Great, thanks. And on that, speaking now more about the rocket, how's the Space Launch System compared to the Saturn rockets used on the Apollo missions?
Once we get to the 130 metric ton version, we will have about 10% more mass payload delivery capability than Apollo had. We will have much more volume capability, particularly when we go to a cargo version with the payload fairing. Keep in mind that even what we refer to as the Block 1, our EM1 vehicle, the 70 metric ton launch vehicle, is still significantly more payload capability than we had with shuttle. So we're building it bigger, and we will evolve the 70 to about 105 metric tons out to 130. Once we get to that 130, we're about 10% larger mass-wise than what Apollo was capable of.
Other questions in the audience? Okay, anything else from social?
I'm getting lots of attention here, thank you. Yeah, this is This is a great question. I think you guys are going to enjoy this one. So what if we use, this is from Chris Fleet, at CFleet47 on Twitter. Could we use the Earth and our moon for a figure 8 slingshot effect for our Mars mission? 140 characters, Cruzan.
In essence, I mean, trajectories that utilize the moon and/or Earth have been used for many missions over years. In fact, our science colleagues frequently use lunar flyby and Earth flyby maneuvers in order to increase relative velocities to get out to further destinations and use it to assist. So, yeah, those are just other trajectories that could be in consideration as we extend out to Mars. Some of our Mars scenarios do actually depart like a direct retrograde orbit, the DRO orbit, into a near-Earth flyby or a highly elliptical flyby of Earth on its departure to Mars. So it doesn't quite look like a figure 8 potentially, but the concept is one that's been used a lot.
If I may, we could, and it's harder, as Jason's pointed out. One of the reasons that we have SLS sized the way we do is it provides us the capability to take missions and go to them more directly, which is more efficient from a time and cost perspective as it's coming out in some of our trade studies.
Okay, thank you very much. Please help me thank our panel, and we'll ask our next speaker to come up. Thanks, everybody. And again, you can find out more information about NASA's exploration program, human exploration, at nasa.gov/exploration if you really want to drill down deeper into what the plan looks like for Orion's upcoming test flight and what SLS work looks like as the rocket and the spacecraft start to come together. NASA.gov/exploration is the place for it. I think there you can also find the video that Dan showed that showcases some of that hardware work that's happening around the country on these. So now I'm pleased to introduce our next speaker. Randy Lillard is the Program Executive for Technology Demonstration Missions in the Space Technology Mission Directorate. Since joining NASA in 2000, he has supported headquarters, the Jet Propulsion Laboratory, and the Johnson Space Center. His previous work includes supporting the Columbia accident investigation and NASA's return to flight efforts. He's also led a multi-agency team to develop the aerothermodynamic environments for Orion, I didn't mess that up, and supported the Juno program office during its launch campaign, any opportunity to plug Juno. A very cool mission on its way to Jupiter. I think it gets there 2016, nasa.gov/Juno has more information about that, but please help me welcome Randy Lillard.
I didn't know I'd help you plug Juno while I was up here. So thank you. This has been some really interesting presentations earlier, so hopefully we'll continue with Space Tech, Space Technology Mission Directorate, showing some of the, be a lot of overlap between what you just heard from our HEOMD friends, which I think is a very good stance for how we are investing for human exploration. Next chart, please. In order to execute an asteroid mission, or in the future return to the moon, or land humans on Mars, we need a substantial and sustained investment in technology. Without this investment in space technology, we're not going to be able to execute these missions when we're ready to go. In other words, we either have to sustain the development now, or we're not going to be ready. The Space Technology Mission Directorate was formed to keep that sustained development moving forward. This chart indicates how the programs we have. We have 9 space technology programs in the Directorate, organized into 3 areas. The first area on the far right is how we are working to create a market for the growing economy. We have centennial challenges. I think you've seen a lot of the rovers and electric airplane challenges. Those have been very successful. We have a Flight Opportunities Program and Small Business Research Initiative, SBIR, utilizing small companies. We have our innovative concepts, the NIAC guys we always call are the ones who are pushing the state of the art, breaking the laws of physics, come up with new ideas for the future. And along those lines, we have grants with many universities, engaging all the universities we can around the country. And our Centerovation Fund, where we get all the best and brightest at NASA to put ideas forward for technology innovation. And finally, what we call our last area of investment is the demonstration for cross-cutting and demonstrations. We have TDM, Technology Demonstration Missions, which is where I work. We have small spacecraft, which is sort of flight demonstrations, but geared towards small spacecraft, microsats and small sats. And we have the game-changing project, which is pushing technology development in the lab to get it ready for demonstration. Within these 9 programs, in the last few years since our inception, we have conducted nearly 50 external competitions, evaluated more than 9,000 proposals, and I believe we actually have one person who's read just about 9,000 of those proposals, and we've selected more than 2,000 of those proposals for award. Within those 2,000 proposals we've selected, that comes to about $900 million in funds going to industry and academia within those proposals. Now, we believe these investments are addressing the high priority challenges for achieving safe and affordable deep space exploration. In fact, in the next 24 months, and we keep an eye on our website to watch this, nasa.gov/spacetech, we're going to launch 7 technology demonstrations, 4 within the Small Spacecraft Technology Program and 3 within the Technology Demonstration Missions Program. And actually, we'll go through some more details on that. Next chart. How we have organized ourselves for the near term, how our investment strategy is we've grouped these investments into 8 technology thrust areas for deep space exploration. Today, I'll go through some of these in detail, not all of them, we don't have time for that. But these technology thrust areas are tightly coupled and aligned with the NASA's technology roadmaps that the Office of Chief Technologist puts out, the Space Technology Investment Plan, or the STIP, and also the National Research Council recommendations on those roadmaps. So all our areas are tightly coupled with all of we see as our customers of where we want to go. The first area, which I'll highlight in more detail, and you've already heard a lot about today, is solar electric propulsion. Here we're looking at building a high-powered solar electric propulsion system using high-power flexible arrays and a new thrusters for high power. We'll go into detail again on that. The next area is space optical comm. I think Sam talked about the need for communications. So what we're doing is a very interesting topic. Is Human Exploration had done the Lunar Laser Communications Demo, LLCD. We're building on that demonstration, taking that hardware. They show that optical comm works. Optical comm can increase the comm capability from 10 to 100 times over the current system. So we take what they did on LLCD. We're going to do that with our demonstration, partner with HEO, to show how to do it in cislunar, and we're going to develop that capability and give it to industry, give it to other government agencies, and then we'll take that knowledge and move it towards deep space optical comm, so we can move that optical comm capability all the way to Mars, so we can get a trunk line back from Mars. And many of the images that Curiosity has taken never get to leave Mars. So the hope is we can get that trunk line back to Mars and actually pull all the images back. The next area is advanced life support. I think after the talk today, I'm going to skip that. Everybody knows how important that is with this crowd. And then move on to entry, descent, and landing. This is an area that we are heavily invested in. Not only doing computational modeling, analytical models, but also inflatable structures and new propulsive techniques to land large payloads on Mars. Curiosity was an amazing 7 minutes of terror. It was a 1 metric ton payload to the surface, so on the order of a car. We need to land 15 to 20 to 40 metric tons on the surface for human missions. So we're looking at landing 1 to 2 story buildings. So we need new technologies to get there, and we have investments in that, and I'll show you one of those today. And then the final one I'll talk about today is lightweight structures. We have a very big interest in composites to help SLS move forward. We think that if we can replace an upper stage for SLS with composites, you can save 25 to 50% of the mass in that upper stage, which translates right back to payload, which would be a huge gain for getting more payload to LEO and to explore the solar system. And the other areas I won't go over today, space with robotics, deep space nav, and observatory systems, that there's more information on our website, and we can get you that if you need it. Next chart. So one of our big investment areas in the coming years, especially this year and next year, is solar electric propulsion. We are planning an affordable demonstration of a 30 to 50 kilowatt SEP system, which includes lightweight solar arrays and a solar electric propulsion module of maybe 10 to 12 kilowatt thrusters. And you can see it's a cross-cutting demonstration. Not only are what we're developing is pushing the envelope for ARM, but it's also pushing it for industry and other government agencies in terms of many applications around. Our plan right now is to demonstrate the SEP module, our tech demo mission on the ARM mission. So we would use the ARM mission to validate the SEP system, the arrays and the thrusters. The impressive thing about what we're developing are arrays. They are half the mass and 1/3 the packaging volume of standard arrays today. So once we replace these arrays, not only for NASA but for commercial industry, we can either provide more power and better volume packaging at the same price point for industry, or we can provide for, say, a science mission. We replace the arrays with the ones we give them, and these arrays can provide ample power to space missions, all the way out to Jupiter. In essence, we still use arrays in Jupiter. So these arrays are going to be a big deal for the industry, and they're going to revolutionize the market. Also, we're developing electric thrusters at NASA Glenn Research Center with JPL. And these thrusters, when coupled with these arrays, are going to really enable all these new missions. In the next 18 months, we have some big plans in SEP. The first one is begin the design and test of the large-scale solar arrays. And what we'll do is leverage the work we've been doing it started in our game-changing project in fiscal year 12, where we went out with a contract for a BAA and awarded two vendors, ATK and DSS, out of California, to build large, on the order of 10 to 15 kilowatt arrays to deploy on the ground. ATK just finished their deployment in March very successfully, and DSS's deployment is coming up in May. And both those deployments both of those designs can be used for the armed mission or for industry. The second area we're doing in SEP is developing these arrays. We're going to be going out looking for design and build engineering units for these high-power electronics and the thrusters for SEP. And again, we'll be leveraging the investment we've been making inside our game-changing project and inside our technology demonstration missions. The last two areas for SEP are large quantity propellant tanks. So the armed mission has a need for on the order of, I think it's 2,000 to 10,000 kilograms of helium, so a very large, xenon, sorry, wrong one. So we had to have huge tanks to get that done, so we're going to be going out the design on that. And we're also working to engage academia for ideas and concepts, as Michelle talked about the BAA. The BAA, she sort of listed the dates when the proposals were due, but we're looking for industry-led studies of how existing commercial capabilities can be used to leverage. We can leverage those to help the armed mission and improve our SEP capabilities to enable all these missions. Next chart. The other demonstration we wanted to talk about today was the LDSD project, which is called the Low Density Supersonic Decelerator Project. I think everybody remembers the 7 minutes of terror for MSL. And again, I spoke earlier, the state of the art for that is 1 metric ton to the surface. Going from 1 metric ton to 40 metric ton is probably inconceivable at this moment, so we're going to take a stepwise approach in how to add more capability to get to Mars. LDSD is developing 3 new decelerator technologies to try to go beyond what MSL did. The first 2 are inflatable aerodynamic decelerators. They're called SIADs, supersonic inflatable aerodynamic decelerator devices. They are essentially parachutes or inflatables that attach to the outside of a heat shield and just make it larger. So you can still stow them. You still stow your heat shield, looks much like Orion or MSL, in the same shroud, but these inflatables can, once you get into orbit and get ready to enter, they can grow out so you have more area for drag. So these are the two of the devices. There's not a great picture on this chart. And the other device is a 30.5 meter parachute for supersonic parachute for Mars entry. The MSL used the Viking Heritage parachute. Viking uses 16.5 meter, I believe, parachute. MSL scaled it to about 21, 22 meters. To deliver these larger payloads, we need bigger parachutes. So we're going through a development effort now to build a 30-meter parachute. This test is this summer in June. We have 1 test this June and hopefully 2 tests next summer of this technology. The trick for testing this technology is at Mars, the density is so much different than Earth. Testing these, dropping them out of airplanes or testing them on the ground, they don't reach the same loads at the same conditions. So the project came up with a unique way to test this, where you take a balloon, I think the largest balloon the science directorate has for their balloon science program. It's on the order of 34 million cubic feet of helium in the balloon. The balloon takes a 3,000 kilogram payload which is the heat shield, a full-scale 4.7 meter heat shield that looks like Orion, with a Star 48 motor in the back of it. It floats that to 120,000 feet. As you can see, the blue line as we move up, it floats to 120,000 feet out of Hawaii. This is at the Pacific Missile Range. At that point, the Star 48 motor ignites and takes the capsule that looks just like a MSL Orion to 180,000 feet, about Mach 3.5, where you see a burnout. The SIAD deploys, so you go from a heat shield to the SIAD comes out, and then that cruises to about Mach 2, where it slows down because the SIAD slows it down. Then the parachute comes out at Mach 2, and then it lands in the ocean for recovery. Now, this project is very exciting because it's going to enable double the payload increase in mass to the surface, but also not only do we add more mass to the surface, but we cover more elevations at Mars. The surface of Mars is obviously very, very hilly and has mountains. This capability can give you 25% higher access to higher elevations. That's about 50% of the surface of Mars. So you get to higher scientific areas of interest with this capability. It also reduces the landing ellipse by a factor of 3. So in other words, the current landing ellipse for MSL, we can shrink that by a factor of 3 by using these new technologies. So if we're trying to land multiple payloads together, we don't have to have a very mobile surface to move them back and forth. We just land them closer to each other. And this technology, again, we'll be testing in June this summer, and it will be ready for infusion into missions as early as 2020. With the hope that it could really enable sample return or some of the precursor missions that our HEO friends talked about today. Next chart. So you've heard of all the thrust areas and some of the investment areas we're in. What I think everybody is always interested in, where are the opportunities for business and industry and academia to work with us? So this chart is sort of where we see our investments for the next 18 months and where those opportunities are for partnership. So as always, we are looking to solicit the nation's best and brightest in academia, industry, and other government agencies to help us push these envelope and push these technologies to where we need to be for deep space exploration. These areas align very well with the thrust areas we discussed earlier. I'm not going to go through them in detail, but we will be having solicitations out in the next 18 months on solar-electric propulsion. In space power, we actually have one out right now for space power, which is seeking proposals for the development of new, more capable energy storage technologies. So we're looking for two things. One, to improve our current capabilities. So at the system level, can we do better packaging? Can we use better chemistry, better cells to increase the density and crank up the power for space batteries? And then the other area for this is very high specific energy devices that will go past the theoretical limits of lithium ion. So both areas are out right now out of our game-changing program. We'll be going out in life support and resource utilization. Jason talked about the Mars 2020 AO. There's a joint SMD, HEO, and STMD proposal out for ISRU on Mars 2020 to break CO2 into oxygen. And I think we talked about how critical that was. And also, we have one out right now for advanced oxygen recovery. So as we move forward with exploring, we're going to have to recycle our air as we get our astronauts out in space. So we have a call out right now on the street for advanced oxygen recovery to enable these human missions. And then we'll be going out with more interdisciplinary landing work, space robotic systems, more optical comm work, and maybe some deep space optical stuff on Discovery. There's a call out for the Discovery 13, which is a 2014 Discovery mission call, an SMD, for deep space optical comm in partnership with them. Lightweight space structures and space observatory systems, again, more work there with SMD. So next chart. All right, so I thank you for the opportunity. We've got a lot of interesting stuff going on this summer. You should watch our website, nasa.gov/spacetech. You should keep an eye. We've got the LDSD test is going to be really exciting. We're going to have hopefully a live feed from PMRF, so keep watching that and watch our website. And again, we look forward to helping our exploration partners in doing these demonstrations. Thank you. Yeah.
I'd like to start, if we could, with social. I think there's a technology question there.
Sure. At CL_Meyer wants to know if we've done any further work on nuclear reactors and improved propulsion to get people to Mars faster.
We are looking at sort of component work on nuclear systems, but we haven't yet made a large investment in nuclear thermal propulsion. So the answer would be we're looking at it, but we haven't done it yet. And I believe, is Jason still here? Yeah, Jason, I believe we're working with AES on that endeavor, if Jason wants to add anything about that.
Yeah, one addition to that is that we are advancing basically the fuels development that is the kind of critical part of nuclear thermal propulsion. So we've been advancing to try to recover our ability to create the fuel sources that are needed for that in collaboration with the Department of Energy. So our main focus has been on fuels development today, not on the actual engine systems to date. But we are looking at it as I was describing earlier, kind of near-term high technology readiness level with our solar electric propulsion while keeping a balanced portfolio of long-term investments like NTP. So.
Go to Frank.
Hi, it's Frank Moore with Aviation Week. On your inflatable decelerators, are they scalable to the size that you would need for a human Mars mission, and what is that size?
Not with current launch shrouds, because you would need, you'd probably need 11, 12, up to 20 meter diameter rigid heat shield for reentry. So we think we can take the current 4.7 meter heat shield that we've been using and probably get an 8 to 10 meter SIAD with that. So we could probably scale it to 8 to 10 meters right now. We would have to do some work on if there's a way to get a larger rigid heat shield in orbit before we could have a larger decelerator. So it's probably not going to have a 20 meter shape like that.
Other questions? Go ahead, Ken.
Hi, Ken Kramer for Universe Today. A question about the solar electric propulsion. I think you mentioned it could have applicability in other areas of the government. Is this just a NASA program, or do you receive funding from other government agencies?
We're exploring looking for other government agencies, but as of right now, the major investments in SEP that we discussed today are ours. NASA alone. But we have been working with other government agencies to see if there's a collaboration. We've sort of been waiting to see when moving towards ARM that we would do it within our own funds, and if something did happen with ARM, we would move towards a more collaborative environment.
Any interest from private endeavors like SpaceX or Orbital or anything like that?
There's a lot of interest from private companies and industry on this. It has to do more with the providers, the commercial spacecraft providers who want the arrays or who want the thrusters than say that we've had discussions with SpaceX. But there is a very strong interest from those companies who want to fly these arrays. I don't think we've got anyone to commit to kicking in money yet. But they will be interested in flying the arrays.
Randy, why is solar electric propulsion such an enabling technology? Why is this so important to our future exploration endeavors?
Well, I think it's a great example from HEO is that when you include solar electric propulsion to take missions to Mars, it cut the number of missions in half for cargo. So it's so mass efficient. It's slower, so it's not great to take humans to Mars, but it's so mass efficient because it just uses, you don't have to have the chemical oxidizer and fuel there. Since it uses just the ionize, it's so efficient. It ionizes the atoms movement so efficiently that it just cuts the mass down by a factor 2 for what you need the launches to Mars. So I think its efficiency is good. The only downside is it just takes a little longer time.
Thank you very much. Any other questions? Let's go back to Frank.
I just noticed that John Grunsfeld is still here. With an increase in the elevation that you can hit with these advanced EDL technologies, what's some of the science that might open up?
It's a great question. When we looked at flying the Mars exploration rovers, there was a site selection team of scientists and engineers who got together and tried to find the safest places for us to land because we wanted to make sure that we got at least one rover on the surface. And with Spirit and Opportunity, we were lucky to get 2. However, from orbit, they kind of looked like boring places and ones that were, relatively speaking, easily accessible. With Curiosity, we tried with the smaller landing ellipse, a much harder place, but still one that was within the performance envelope of the sky crane and the supersonic parachute. We're now having discussions, in fact, Michael Meyer is here, about landing site selection for future Mars missions, including Mars 2020. And partly because we now know the performance of the heat shield due to the Medley instrumentation, that was a cooperative effort, and the parachute, and also just the Mars atmosphere seasonally, we'll be able to go to an even more challenging place, higher elevation perhaps, and perhaps shrink the landing ellipse. And that's very important because you want the rover to get close to the place that from orbit at any rate, the mineralogy and the other applications that you want are close. We're going to spend the better part of 2 years driving to Mount Sharp along the way doing science, but getting to the place we really want to be. And certainly for a human space flight in the future, you want to be very close to whatever habitat or fuel systems you've already in place. And so the supersonic decelerator is really critical for future science missions to get to higher elevations, or perhaps in some cases to get to very small landing ellipses at lower elevations. Valles Marineris, for instance, if you wanted to go down to the bottom and measure, like we do in the Grand Canyon, the history of Mars. These kind of places will require small landing ellipses so that you land on Mars and don't crash on Mars.
I'll ask our chiefs to take the stage as we help thank Randy Lillard for his presentation. Thank you, Randy. And again, we have some, as Randy said, just some incredible testing coming up on space technology. And of course, you can find out more information about that, as Randy said, at nasa.gov/spacetech when those tests come around. I know we in public affairs are looking forward to helping tell the story, and you'll, of course, find out more information on nasa.gov as we get closer to some of those incredible tests. So I'm pleased to now introduce our chief scientist and chief technologist who are presenting together. Ellen Stoffen was appointed NASA's chief scientist in August of 2013. She serves as principal advisor on the agency's science programs and science-related strategic planning and investments. Previously, she was vice president of Proximy Research in Maryland, an honorary professor in the Department of Earth Sciences, the University of College London in England. Her research is focused on the geology of Venus, Mars, Saturn's moons Titan, and Earth. She's an associate member of the Cassini Mission to Saturn radar team and co-investigator on the Mars Express mission's Marsis sounder. Her appointment as chief scientist marks a return to NASA for her from 1991 through 2000. She held a number of senior scientist positions at NASA's JPL, including chief scientist for the New Millennium Program, deputy project scientist for the Magellan mission to Venus, and experiment scientist for CIRCE, an instrument that provided radar images of Earth on 2 shuttle flights. Next to her is, as we just announced last month, as a matter of fact, we just announced David Miller is the agency's new chief technologist. Most recently, he was professor and director of the Space Systems Laboratory at the Massachusetts Institute of Technology, MIT. Prior to this appointment, he held various positions on NASA projects, including principal investigator for the Regolith X-ray imaging spectrometer, the OSIRIS-REx asteroid sample return mission, planned to launch here soon, the next couple of years. He also was the principal investigator for the synchronized position, hold, engage, and reorient experimental satellites. You might know it as Spheres, very cool project. We have great video of Spheres moving autonomously on the International Space Station. And most recently, he served as the vice chair of the Air Force Scientific Advisory Board. Please help me welcome Ellen Stoffen and David Miller.
Well, thank you. And Ellen and I are going to tag team this presentation. So what you've seen here today is that the road to Mars really involves much more than one mission directorate at NASA. It involves the careful integration of scientific discovery, technological innovation, commercial development, international collaboration, and the human imperative to explore. Therefore, all 5 of these endeavors have essential roles to play on this human road to Mars. Can I have the next? Oh, can you go forward 2 slides now? Thank you. So while I was growing up, I was very fortunate to be able to watch firsthand NASA's development of a lunar exploration program. And while many differences exist between now and then, there are some important parallels that I think we can draw. For example, during During the Mercury program, NASA developed the capability to get to and survive in low Earth orbit. Through Earth Reliant, we're identifying and solving the challenges of long-duration spaceflight and doing that through the activities on the ISS. During the Gemini program, NASA developed the capability to live and work in space and develop the technologies to help them do so. In the Proving Ground, NASA will develop the capabilities to live and work during long-duration spaceflight. During the Apollo program, NASA developed the systems that allowed humans to explore the moon. And in the Earth Independent, we're developing the capability to explore Mars. Except there's one key difference, and that is this time, unlike Apollo, we're taking a sustainable and pioneering approach to that endeavor. So all 5 endeavors, science, technology, commercial, international, and human, play coherent and essential roles in developing these capabilities. Next slide.
As you've been hearing today, the road to Mars is extremely scientifically rich. Starting right here in the Earth Reliant phase, where the research that we were talking about earlier that's being done right now on the International Space Station to try to better understand the effects of microgravity, the long-term effects of human spaceflight on the human body. That's helping us not just get ready for Mars, but it's also teaching us a lot about the human body. The way that our systems function so different in microgravity is something that we're able to then turn around and apply back to Earth, from loss of bone density to muscle wasting that occurs on Earth orbit. We're able to start to address those risks that we need to get humans to Mars, but we can turn around and take that information to help us back here on Earth. In the Proving Ground, Michelle was talking about the Asteroid mission and the survey that we're doing, the detailed survey that we're doing to try to better understand the population of near-Earth asteroids. Asteroids are such an interesting solar system materials because they're that materials that we're made of. The Earth is made of that basic material that's found in comets and asteroids. And to be able to go out and have a much better understanding of the population of asteroids, we can then start asking what they're made of, and then better understand those materials that actually made up the Earth. And in terms of Mars, as John Grunsfeld explained earlier, we are already pioneering Mars. We have been for years. We've landed 7 times successfully on the surface. We've learned so much about Mars, and we're gaining more and more confident that Mars did have habitable environments in the past, and to take that next step and figure out, did life evolve on Mars? What is the nature of that life if it did? Is extremely scientifically compelling, and we are making progress on that every day with Curiosity as it moves up Mount Sharp, getting better and better science. That's just extremely important and groundbreaking. With the InSight mission that we'll have in a few years, understanding more about the interior of Mars, the MAVEN mission looking at water loss, we're really, again, looking at Mars as a system from the interior all the way out to the top of the atmosphere to better understand what happened to that habitable environment on Mars. Can we better understand it in order to answer that very, very fundamental question of are we alone? And so going to 2020, again, going that next step, possibly caching materials, looking forward to, can we at some point nearer in the future return samples back to the Earth? How can we use the Mars 2020 mission not only to do amazingly high quality science at Mars, getting at this question of habitability, but how can we also then move to that next important step of getting astrobiologists, getting geologists onto the surface of Mars to find that evidence of past life. So moving forward, as we have with Curiosity, as we will with 2020, and then in the missions that we formulate beyond that, using Mars missions not just to advance our science of understanding Mars, but using them to take those next steps to close those strategic knowledge gaps from the nature of the dust to the nature of the atmosphere to make sure that we can get those scientists safely to the surface of Mars. And I will say all that work is not just taking place out at spacecraft. It's taking place in laboratories all around the country. There's a huge amount of Earth-based research that goes into not just understanding the effects of radiation on the human body, but to our fundamental research that we do trying to understand Mars. Extremely rich science going on, and it's a key part and an integral part of why and how we will pioneer Mars. Next slide.
So to pave the way to Mars, NASA's technology investments are answering a number of questions. You've seen a lot of the technology portfolio that NASA is working on now over the last few talks. Something I'd like to add is that NASA is being careful to ensure that these technology investments are being made in a way that not only helps pave that way and enable that mission, that exploration and pioneering of Mars, but it also supports other space sectors as well as applications here on Earth. I want to point out also that these technology investments are not just plans. These things are happening right now as we speak. Next slide, please. So to grow the space economy, NASA is partnering with the commercial sector to answer some key questions. As we transition from exploration to sustainable pioneering, it's essential that NASA partner with the commercial sector for many reasons, 3 of which are to lean out through commercial practices the costs of traveling the road to Mars. Second, to provide more opportunities for innovation by emerging entrepreneurs. Third, to spin off discoveries, capabilities, and technologies for the benefit of sectors back here on Earth. So I'd like to draw an example where, as in comparison to the days of the NACA, when collaboration between government and industry was essential in recovering aeronautics for the United States, basically a leadership we had lost at one point. Such collaboration is essential today to sustaining our role in space exploration. Next slide.
As we've heard about today, this is not just a path for the United States, it's an international path. We will not do this alone. We must do it with the nations of the world, and we are actively working with those other nations in formulating the global exploration roadmap. Other countries are anxious to participate. And again, this isn't something that's theoretical, it's something that's occurring right now today. From the International Space Station, where we work very closely with our international partners on this research that I've been talking about to understand the fundamental effects of microgravity, not just on the human body, but doing all these preparatory research to get us out to Mars. That international collaboration is taking place even as we speak. The search for near-Earth asteroids is an international effort. It's not just a U.S. effort. To the international work that we have done for years in exploring Mars, from the Mars Express mission to the many, many examples of international participation on our many other science missions at Mars. So this is not a U.S. path, it's an international path, and we're working very closely with our partners to try to best understand how to use everyone's capabilities, everyone's resources to try to do this together. And I will say also, David was talking about commercial partnerships. These are international partnerships. Every time I go out to a school, I look out at them and say, we're going to be doing this in the 2030s, and you guys need to come help us. You need to go back to your math class and your physics class and work hard, because I think this is an also extremely motivating program to engage kids in science, technology, engineering, and mathematics. Next slide.
So NASA's human road to Mars entails a methodical development of capabilities that answers a number of questions. No one can expect to successfully complete a challenging task if they haven't studied and practiced first. So we need to understand what works, what doesn't work, and how to deal with things that no longer work. This takes practice, and this practice must be done in an authentic way, and needs to be done across all 5 of these endeavors. So like the Mercury program, the International Space Station allows us to study what works and what doesn't work. Like the Gemini program, the Proving Ground allows us to practice with those capabilities that do work, honing our skills, and deal with them when they no longer work. This is key. This methodical interplay between science, technology, commercial, and international endeavors is essential in successfully and sustainably moving humanity along the road to Mars. Thank you.
Questions from the audience for our chiefs? Let's go to Ken.
Ken Kramer for Universe today. Ellen, yeah, you raised exactly the question I wanted to ask about international participation. Okay, so the U.S. is going to provide the SLS and the Orion. Can you give some examples of what the international partners could provide? What are they interested in providing?
Well, that's something that's a subject of ongoing discussions, and Gerst could probably give you more specifics than I could. But for example, again, the work that we're doing right now on the International Space Station in terms of looking at the long-term effects of spaceflight on the human body with the one-year mission the twin study that we're about to embark on. We are working very closely with our international partners, and they're very interested in that research and in participating in any way they can. So that's a near term. Again, on Curiosity, we have foreign investigators or investigators from many countries participating in that. Some of our partners have looked at maybe being interested in going back to the surface of the moon, which is not something that we see on a critical capability path. If they are interested in doing that, we're certainly interested in aiding them in any way we can, even though that's not on our main path. So, Gerst, I don't know if you want to. No, he's shaking his head. No, those are the sorts of things that we're talking with them about. But again, we're very much in the discussion stage. But there is a booklet that you can get somewhere on the web, the Global Exploration Roadmap, and that very much is a multi-agency product. It's not just a NASA product.
Okay, I think we have a really tight schedule for our next speakers. Unfortunately, I think I'm going to have to leave it at one question. Maybe if the chiefs can stick around, if we didn't get to anybody's in the audience, we'll ask them to. But please help me thank our chief scientists and chief technologists. So here to provide concluding remarks is Robert Lightfoot. He is the Associate Administrator for NASA, which is the agency's highest-ranking civil servant position, and he took this position in September of 2012. Previously, he was Director of NASA's Marshall Space Flight Center in Huntsville, Alabama. That, of course, is one of NASA's largest field installations, playing a critical role in NASA space operations, exploration, and science missions. He's managed a broad range of propulsion, scientific, and space transportation activities contributing to the nation's space program. From 2007 to 2009, he was Deputy Director of Marshall in previous capacities. He's managed the Space Shuttle Propulsion Office at Marshall. He was the Assistant Associate Administrator of the Space Shuttle Program here at NASA headquarters. He directed the Propulsion Test Directorate at NASA's Stennis Space Center, and he began his NASA career in 1989 at Marshall as a test engineer and program manager. Please help me welcome Robert Lightfoot.
Well, good afternoon. I want to thank you all for being here today. I know you heard from Charlie this morning. You know, today was intended to provide you the insight into our ongoing exploration efforts, and I caught the last part of Ellen and David's presentation, and I think that you got plenty of insight into what we're thinking. Our stepping stone approach to take humans to Mars includes efforts in all our mission directorates, the space mission directorates, science, space technology, and human exploration. This integrated approach offers us some interesting challenges from time to time as we deal with our budgets and we deal with the process as we go forward, especially in an environment where we as a team think a lot about one-off missions, right? We think about this mission and that mission, but the way the guys have put this together and the way the teams have put it together is a really integrated approach to how we're going to attack this. And when you see how we're approaching this, you see this path to Mars, you begin to see how each effort is stitched together. You know, each piece has a common goal of getting humans to Mars, so that we are ready to get there. So when you think about it, and I'll just kind of repeat some of the things you've heard today. You talk about Earth dependent. You talk about the International Space Station and what we're learning there with the technology, the science, and the reaction of the human body to being in space. Those kind of things are critical for us if we're going to take explorers beyond low Earth orbit. That, of course, is supported by our commercial cargo and hopefully our commercial crew efforts soon, right? This is what we're doing. This is how that allows us to tackle those critical challenges. Then you look at the proving ground as we talk here, the area around the moon. Our asteroid redirect mission fits right in there. It allows us to try operations and practice and do things that we're going to need to do, but we're close enough to home to get back if we need to. And that's another piece that's critical. In that area, what do? We get to test a lot of the things that the Space Technology Mission Director is working on. I mean, the things that we need for solar electric propulsion, things that are going to advance us and allow us to go to Mars. In that arena, we also think about things like radiation protection. We think about entry, descent, and landing. We got a big challenge there if we're going to Mars with humans. What are we going to do there? So our Space Technology Mission Directorate is really involved in that. And then when you start talking about Earth independent or Mars ready, right? When are we going to be ready to go to Mars? What are the things that we've got to go do? All our efforts today, all our efforts that you heard from these guys, we're trying to make sure they're extensible. We sit in meetings all the time, and my question to them all the time is this a one-off, or is this going to help us? Is this that takes that next step as we go to Mars? And so it's all about optimizing around the goal of getting humans to Mars, as opposed to maybe optimizing around a given mission. And that's a challenge for us. That's a challenge in our thinking and the way we go. But this team's ready, and they're up to that challenge, and I think you heard it today from every one of them. They're thinking this way, and we're pressing. So I hope today was useful for you in terms of providing that integrated insight into this exploration strategy. We want to hear your feedback and comments. I mean, honestly, that's why we have you here from that standpoint. To us, this is the beginning of a continual dialogue, a dialogue we want you to be part of as we take these steps. You know, if you look, the journey we're about to take will take many steps. We talk about the International Space Station as one of those steps. You heard today what that does for us. We talk about our advanced exploration initiatives that Jason's working on. Those are a set of steps. We talk about the Asteroid Redirect mission. That provides us a set of steps. All those steps are going to be important, and there are going to be more. You know, there are going to be more that aren't on our plate today, but all of them will be focused on getting humans to Mars. And I think that's going to be real important. So I want to thank you all for joining us here today. And I want to thank the speakers. These guys took a lot of time and did their talks this morning. And I hope you got to see that insight and understand what we're trying to do from a strategy standpoint. And I'll just close with this. We're on a path to Mars and getting humans there. That's what we want to go do. Is that bold? Yeah, it's very bold. It's what we should be doing as an agency. And all we ask is that you come along for the ride and join us in that strategy and that journey. So thanks again for being here today, and thanks to the teams that presented.
You have time for one question, maybe? You have time for a question?
Sure.
All right,
I'm sure the JPSS team will be glad that I'm down here.
One question. Frank, do you have one?
Don't give it. Don't force him.
Well,
come on, Trent.
Actually, I wanted to ask Charlie. You know, you're talking about way out in the future, and there's a lot of discussion about international cooperation, commercial cooperation, at a time when neither one of those things seems to be in the forefront, particularly with your Russian partners. The commercial sector's kind of in an uproar this week. How do you get past the short-term blips, let's hope they are, to do the long-term objectives that you're talking about?
I think for us, it's pretty simple, Frank, is a consistent approach and a consistent message and a consistent cadence toward making each one of these objectives become real. I believe our international partners have been very participatory in this, regardless of what you hear. From a space standpoint, we seem to have great participation and haven't really seen a change at all. So for us, it's just that consistent approach, that consistent challenge between the three space-based mission directorates to make sure we're focused on the same thing.
Okay, please help me thank NASA Associate Administrator Robert Lightfoot. Thanks, sir. And just a reminder that you can find out more information about NASA's human exploration path to Mars at www.nasa.gov/exploration. It's our goal to have all the presentations you saw here today up on nasa.gov/exploration later as the electrons allow. We'll see how fast we can do it. And of course, we'll have archived video of this event available on nasa.gov and on NASA's YouTube channel later today as well. That, of course, is youtube.com/NASA television. Thanks to all of you for participating. Really want to just take a special moment here to thank our speakers. It was an awful lot of time and a lot of leadership here in this room. I really appreciate you making the time to come tell us all about the human path to Mars. So that's going to do it for today's event from NASA headquarters. I'm Public Affairs Officer Trent Parado. Thanks for joining, and we'll see you next time.